Hi everybody, and welcome to day 2 of the WeAreDevelopers Mobility Days brought to you by Volkswagen. So, my name's Stefan and I'm your guide through today's sessions. And since this is day 2, you also have the option, if you haven't seen them, to see the recording of day 1. But don't do that now, because now you're here and you are waiting for Joachim. But before we get to that, another thing, what can you expect today? So let's have a look at the agenda. So let's start off with Joachim, who will tell us how to bring together the best of two worlds, enterprise-grade Linux to vehicle. And after that, we'll go into model-based system engineering in an agile product development process together with Daniel and Hermann. And after that, we will join a panel discussion about the mobility industry and if it will tilt towards infrastructure. This will be together with the two Michaels, Jana, Sergei and Daniel. And after that, we deserve some really interesting slip through the boundaries of legacy systems with Kotlin and Spring WebFlux, together with Alberto and Lucas. And the last talk of the day will be how to implement continuous delivery in a data processing pipeline, together with Alvaro, which will give us a clear picture. At least it will give me one, because that's a thing I am struggling with. So that's this. And now you're saying, okay, what is this with the Q&A sessions and stuff like this? So it's simple. On this side of the screen, if you are on wearedevelopers.com/live, you will have the Slido box where you can ask questions, and speakers will answer these questions at the end of each talk. Right now, let's just try it out, and some of you already did it. Let's see, where are you from today? Okay, Vienna. It's a lot of people from Vienna. I think a lot of people. So, and we have Berlin, Germany, and I cannot read this. It's so small on my screen. Can you read that, Gary? No, you cannot. Well, I think you can read it on the webpage even better. It's also a thing to try it out, and also to let everybody who is watching know that they are not the only one watching, and especially the speaker. Because imagine you are the speaker, you do not see the audience, so you're basically talking to a camera, which is a strange feeling. If you want to try it out, try it at your next Zoom call. So, but before I finally bring you to stage to meet Joachim, our first speaker, let me tell you something about something very important, and that's the code of conduct. We love it and we value it, and you should too. There is a short version which is basically be respectful, play nice, and behave more or less. Yeah, there is nothing about a good discussion, but there is a border. This was more or less the long version. Or was it the short one? I think that was the short one, because this is the long version. And now that we know everything about the event, let's start and head over into our first session, which will be Joachim Werner talk about the best of two worlds, bringing enterprise-grade Linux to the vehicle. Hi Joachim.
Hi Stefan. Thanks
Now
for
the
having me.
stage is all yours. You're welcome. See you at the Q&A.
Thank you. So, you probably have heard this term quite a few times when it comes to technology. Oh, that's not rocket science. I can do this. But sometimes technology really is rocket science, literally. Like if you want to bring rockets like this, the Falcon Heavy, to the sky, and even more impressively, bring those boosters back exactly on the pad or on the landing vessel. Now, if you haven't heard yet, behind the scenes, what's going on is a lot of the stuff running in these rockets is actually based on Linux. So there's a Linux running, and I think this shows that even for the most mission critical, safety critical applications these days, Linux can be the answer. So as Stefan has already introduced me, I'm Joachim Werner, or Joe Werner. I'm the principal product manager for Automotive Edge at SUSE. Joined SUSE in 2004, so have been with the company for about half of its life, or more than half of its life already, in various roles from project management to product management. But I also have a bit of an engineering background, had my own software company before I joined SUSE, of course, doing open source stuff. Yeah, our vision at SUSE is to simplify, modernize, and accelerate. We want to help our customers to simplify how they run their businesses, simplify their IT environment, simplify their solutions, allow them to modernize, transform business processes, sometimes very disruptively. And you'll see how this translates to mobility industry, to the vehicle in a minute, and also accelerate. If you think about acceleration, yes, of course, cars, are all about speed, but also think about bringing new features to cars. This has always been a bit of a problem, and I'll get to that in a minute. And again, we think with our solutions, with our open source background, we can help a lot with accelerating how customers can bring solutions to the vehicle faster. SUSE, we are talking about the power of many. That's the power of many of our own employees, contributors, friends, but also all the communities that we are part of. And together with those communities, we now have a broad spectrum of offerings that are not just Linux. Of course, Linux is still at the core, and that may have been how you've heard about SUSE in the first place, maybe running a Linux distribution on your laptop or so, or in a data center. But these days, Linux is only part of the offering. On that upper left-hand side, you see our software-defined infrastructure, software-defined compute, storage, and networking. That's the basis for bringing these container and cloud platform services to the hardware, and that's about running containerized solutions on site, in the public cloud, in multi-cloud environment, and also at the edge. So if you haven't heard that term edge yet, edge is basically about computing that's not in a central data center or cloud, but closer to where data is processed or where actions have to be taken. This could be in a telecommunication facility. It could be small mini data centers on site in a factory, but also the far edge, let's say a car or truck. Yeah, and finally, just recently, we have started to work on solutions that bring open source artificial intelligence and machine learning technology to our users. Today, we are going to focus on that upper right corner, the edge computing, and in particular, of course, the far edge, and bringing compute to the car. So, as I've said, I've been with SUSE for most of the almost 30 years now that we are doing open source software and bringing open source solutions to enterprise customers and supporting them with their mission critical workloads. I was part of the team that worked with SAP in 2008 and after that. These days, not only SAP itself is running on SUSE, but a lot of the most mission critical services, including things that you may not even expect. So if you go to one of the big web shops or so, chances are behind the scenes at some point, your data will hit an SAP system that's running a SAP HANA database on SUSE Linux, for example. And just recently, we've announced yet another step. We announced that we have the intent to acquire Rancher Labs. Together with Rancher, which is one of the most well-known and established open source tools and frameworks for managing hybrid clouds, managing container solutions from the edge to the core to the cloud, we will have an even more complete portfolio from the Linux to the management stack. As this is still pending regulatory approval, I can't really go into more detail, but I've linked the press release so you can look into that blog post if you want to learn more. Yeah, coming back to open source. As Gartner stated last year, open source is becoming the backbone for driving digital innovation. And that's not just in the data center, it's really from consumer electronics, from your mobile phone experience to actually rocket science, as you've just seen. And SUSE is part of that in many places. I've just picked a few that are kind of related here. So in automotive, of the 15 largest tier 1 automotive vendors, 12 are running SUSE Linux. One of them soon even in the car already, and that's what we are talking about today. We are also really strong in telecommunications, and I've put another one in aerospace, so both military defense and civil aerospace. Lots of customers rely on SUSE Linux. What we're talking about today is a relationship that we just engaged with in the last couple of months. So March, April, we closed an agreement with Elektrobit, a fully owned subsidiary of Continental, to develop Linux for autonomous vehicles. Not just autonomous vehicles, but that's obviously the goal, to have Linux in the car that's safe and secure enough even for advanced driver assist features up to fully autonomous cars. Elektrobit has more than 30 years of experience in the automotive software market. More than 100 million vehicles and more than 1 billion ECUs and devices are running software written by Elektrobit. And we are proud to have this partner and to jointly develop this solution where we bring the best of our experience with open source and Linux together with Elektrobit's experience in the automotive market. Those are really two worlds. So our world at SUSE is the data center, something like that. And then there's automotive. I've deliberately picked a picture that doesn't really fit into this room because at a first glance, those are very different worlds. So let's have a quick peek into a typical EE architecture in a car today. So this is like current generation cars that are already on the streets. Usually you will have up to 100 dedicated computers or ECUs, sometimes just running a little real-time OS. sometimes already running Linux or something similar, like a QNX or VxWorks or whatever. Just the wiring harness in such a car together with those compute units can weigh up to 80 kilos. So that's the same ballpark as the electrical engine in an electrical car. And that's where the the acceleration comes in that I had on one of my first slides. You usually get what you've bought. So if you have bought a car 5 years ago, chances are that the navigation system and the whole infotainment is kind of outdated, and you may not get any updates for that. And that's because of the way stuff has been developed. There was a project for bringing an infotainment system into that particular model, and that's it. Yeah, it's very hard to update. Of course, there are a few exceptions, and we'll get to that later. But of course, it's a pity that you, I don't know, spent like 1,500 euros on your navigation system or infotainment, and now your mobile phone has the better navigation. Yeah. Also, cars are very different from traditional IT. You have different network systems, bus systems, signal-oriented versus data-oriented. So you have CAN bus, FlexRay. Yeah, so it's not really the same world that SUSE has been working in. Let's look at that world a bit. I'm picking a retailer as an example. So we have, let's say, an SAP backend system in the data center, finance systems, ERP, and so on. Then there are lots of stores connected via the internet. The whole network is basically plain Ethernet, of course. That's TCP/IP-based standardized networks. In the store, there may be a branch server and then lots of other devices, kiosk systems, cash registers, point of service, and also other like camera systems, whatever. And of course, there's always an internet component. There's some cloud services. Customers today expect that you can check availability of products via your mobile phone, maybe even in the store, use your phone to get additional data or take part in a bonus program or a loyalty program, something like that. So obviously, this whole network has to be highly protected. You have to have user management. Customers have accounts on your central servers, and this has to be secured across the board. Now, in a more futuristic or modern EE architecture in cars, things look a bit different than in that first picture that I showed. The number of ECUs is going to be reduced. So a lot of the compute power is centralized on one or just a few central compute clusters. Then there are so-called zonal ECUs. So basically all the sensors and actuators in a certain zone of your car, let's say your left door or your front end, are connected to one of those zonal ECUs. And the network becomes more similar to a traditional data center network or wide area network, where you have basically an Ethernet ring backbone that transports all the traffic, be it camera data or just signals from sensors and actuator commands on the same unified network. That makes wiring much lighter, up to 20, 30 kilograms lighter. So that's a lot, looking at the 80 kilograms that the traditional infrastructure weighs. And also because you can now connect more or less dump sensors and actuators to logic that's running on one of those central computers, you can add more features as a software. So you can have software-defined features and update those over the air, over the internet connection. So when you look at this picture, look at how this looks. So you have the central Ethernet backbone. You have an internet connection for over-the-air updates, but also because customers, of course, want to have features like being able to check their charging status of their electric car on the phone, or start the air conditioning half an hour before they actually enter the car. Yeah, this is kind of similar to the picture that you just saw. I mean, of course, I deliberately painted it in a way that it's a perfect overlay. But a lot of the technology that we see in this retail store example now translates really nicely into the car example. So you have all those different kind of independent branch servers, if you want, in the doors, in the front end, back end section of the car. The connections have to be secured because people could technically, you know, access your network somewhere in this backbone. You have internet connectivity, you have user accounts that have to be managed across the board, and so on and so on. And that really led us to the idea that as SUSE, with all the experience we have in data center and distributed compute environments like retail or banking or so, we can also contribute a lot to modern automotive platforms. What we are calling from the edge to the core to the cloud, or in the car example, rhyming even better, from the core from the car to the core to the cloud. And as you can see from this picture, we are not just working in automotive. We have customers in medical care, in industrial uses, retail, and so on. But of course, today we are mostly talking about automotive. But first, let's have a look into Linux in general. Linux is everywhere these days, from air traffic control to stock markets to, of course, all the mobile devices, your iPads, your mobile phones, and also aerospace and rail transportation, many different use cases. And the value of open source really is all about how the power of many, how all those contributors, and it's so easy to contribute because you don't have to sign off, you know, lengthy contracts or get hired by a company. You can start small, or as a customer, you can easily switch from just consuming stuff to contributing back. Then there's no real vendor lock-in. Of course, all of us as open source companies try to convince you that our way of doing things is best, but it's not about locking you in with expensive licenses or so. It's about the actual service and support that you get. And if you don't like it, you can go somewhere else. And the other thing really is that standards are not defined by standards bodies. Standards are, in many cases, defined by doing things, by customer-driven standardization. So several customers, let's say several automotive OEMs, decide that they want to agree on certain standards. They just start working on an open source project. And sometimes this gets more formalized and sometimes it doesn't have to. And there's a lot of agility in this whole thing. So just a few numbers. There's a new Linux kernel every 8 to 10 weeks. And there are millions of lines of code that are moved. In this case, for example, about 80,000 commits from 4,000 authors. And the change rate is like 8 changes or 8 to 9 changes per hour. And it's all under an open source license. Now, why would you use SUSE Linux in the car? You may have heard that there's so many other Linux options, embedded Linux options, and so on. But I think that things are changing with the safety and security requirements. A lot of the early approaches don't really fit too well anymore. I think the most important part here is that first line, from project to product. In many cases, developing software for cars is still a project. And that's what we had on the earlier slide. You know, your infotainment just after 5 years, 6 years, it's so rotten. I mean, it's really an old product that you don't want to use anymore. And that's why it was started in many cases even long before the car was delivered, and there were no updates. So bringing standardized products to part of the stack, like the OS, to make it easier to say, okay, well, I don't have to always start from scratch. I don't have to download this and then compile my own kernel and modify it and adapt it to the hardware. But using software that can be used on multiple platforms, and it's pre-built, it's binaries already, that's really the benefit. And data centers and data center customers ran through all those problems before. So why do you have to learn from that again? Just use those proven approaches. I remember in the early days, people would still compile their own kernels, compile their own web servers to optimize little things. And these days, you can basically look at all the standard server hardware platforms from all the major vendors, and they are certified on SUSE Linux Enterprise, for example, and stuff will just work. And also security updates. We provide security updates for up to 18 or 20 years without breaking certifications. And we are a one-stop shop when it comes to getting open source software. So it's not just, oh, I get my Linux base from here, and then I have the BSP overlay, the board support pack for the hardware support, and then I have this and that. We can provide both fully supported and community supported Linux and open source stack software that all works together. That's all built in a single build service for all those hardware platforms. And we have a really proven track record, and we are here to stay. So we have been doing this for almost 30 years, and the plan is to do it for many, many decades from now and support our customers. Not everyone can say that. And we are financially really sound, even in these critical and difficult days. We've had record numbers this year. I just want to pick one of the statements from earlier. So BSPs, the board support packages. We think this approach is ultimately evil. It's a bit like in the early days of your Windows 95 or so, when you got your driver CD for your graphics card or your mouse or whatever. And that was the only time you got an update, or you basically didn't get an update. You just got the original driver. And then once you switch to, let's say, a new version of Windows, your driver wouldn't fit anymore. And then there came signed drivers and things got worse until more and more of those drivers were built into the OSs. And for Linux, this is even more impressive than on other OSs. Basically, all the drivers are kind of built in. But for the embedded world, we still have these overlays. So the board manufacturers come up with their own hardware support, and this makes things much harder in the long run. Yeah, we think that's the wrong model. Of course, we have to convince a lot of people in the industry to change to a more upstream model where they work on those upstream projects, but that's really our mission in a way. So one of the things that really are so much different in enterprise Linux than in embedded Linux in general is how we can use a multi-layer quality assurance approach. And that's also kind of the magic why we are able, together with Electrobit, to aim for a safety certification for Linux. So there are the upstream open source projects, of course, that everyone else can also choose to use directly. And they have a lot of their own testing, unit testing, build testing, whatever. Then we have the OpenSUSE community releases. And there are two types of that, a rolling release called Tumbleweed and one called OpenSUSE Leap. And there is fully automated integration testing. So there are two rings, like first software has to be tested on its own, and then there's integration testing before every release, and those releases are almost daily for OpenSUSE. So it's a rolling release with always the latest, and everything is automated and tested, and things are fixed before they get released in these open source community releases. So the quality is already really decent. It's good enough to have your daily driver laptop running on OpenSUSE Tumbleweed like I do. And then there's SUSE Linux Enterprise. That's when we take this open source and community tested code to the next level, where we have fully tested enterprise level releases, and all the updates go through lengthy testing. We then, for the automotive project, pick only the most stable stuff and have a very limited set of updates that go into the automotive platform. And then again at our partner at Electrobit, when they integrate this into EB Corpus Linux as the product name is on Electrobit's end. There's a lot more testing and integration. And then of course, we also come with the tools that the OEM, the automotive manufacturer, can use to run the exact same test infrastructure that we have, that Electrobit has, again, on site for their own integration testing. We have addressed quite a few of the challenges of edge computing, and I'm just picking a few, and you'll see that most of that is also interesting for the car. So in many cases, when you run edge data centers or computing, let's say in a retail store, there's no full-time IT staff on site. So you need remote management. And obviously in the car, it's the same thing. You don't expect the driver to be able to fix things. The days of the chauffeur that knows how to fix an engine are long gone, and same is true for IT. You don't want the user to fix stuff on the car computer. Systems may be set up by a customer or logistics contractor. Yeah, right. So basically, anyone in a garage has to be able to do the software update, and then of course, ideally, not everyone is there yet. You can do over-the-air updates. Large-scale deployments. Some of our customers have millions of cars shipped every year, and that's really large scale, same as in other industries. And then factory preloads, obviously. Yeah, that's almost, I mean, that's a given for automotive, because the cars are built on the conveyor belt in a factory, and they need to be preloaded with the software there. And it shouldn't be, it shouldn't take hours or days to do so, but it has to be a very quick and efficient process. Then the initial deployment, once that's happened, there's a trust issue. Just like your mobile phone has to uniquely identify against the update network of your phone manufacturer or your network provider, a car has to be uniquely identified, because you don't want modified cars that are not up to spec, that maybe not have a certification by, let's say, TÜV in Germany to connect to your network and get updates. You need to configure your cars. Sometimes features are software defined, like the customer hasn't purchased that feature, and the update shouldn't go out for that feature. And then, of course, over time, you need patching and over-the-air updates and so on. And then finally, monitoring. Modern cars are collecting lots of data that is used for telemetry, for predictive analysis. So this is really a story that I didn't build for the automotive industry. This was a pitch that we had originally prepared for other edge scenarios, but it's to the point. And the product that we are building for that market, the SUSE MicroOS, has a lot of the features that you'll also need in automotive. Like, it's predictable, it's not altered during runtime, so the whole system is basically read-only. You can roll back to a known good state by just rebooting. It's very scalable, and it's reliable. I'll just very briefly go through those highlights, because, as I said, this is not automotive specific. Very minimal footprint. Actually, for the actual car project that we are working on with Electrobit, the footprint is even smaller than we have in this MicroOS. It supports Intel and AMD and ARM architectures. Again, that's important for automotive. A lot of the automotive platforms are ARM 64-bit. It's immutable, as I said, read-only with a health check. So next time you reboot and something went wrong with the update, it will automatically roll back. Currently in the car, somewhat different stacks are used, but a lot of the concepts carry over. We have the SE Linux security framework, exactly as we have in the car solution. And yeah, we can update with small updates. That's not always the same in the car, because they sometimes want, fully encrypted firmware updates. But we are working on bringing those Delta updates to the car as well. Yeah, just picking a few of those. And then there's containers. I'll get to those now. Most of the modern software stacks are using workload containers on top of an operating system, usually Linux, because a container is a very nice way of putting exactly what the application needs into a box and shipping that box. And basically the developer knows, okay, if my container has worked in my on my laptop or in my test environment, it will also work in production. This is what we are doing with MicroOS, and it's also part of the story for automotive, for adaptive AutoSAR, but also more revolutionary concepts where we are thinking about really running setups similar to what you do with Kubernetes in the data center on the car. I've just picked a few of the options that you have for managing those containers. In the car, we're currently using systemd nspawn. That's the most lightweight way of starting a container with just the Linux system daemon. Then there's Podman that allows you to already start containers as so-called pods, so several application components in a single configuration with its network and the ports that should be open and how they connect, like the database connects to the backend server and so on. And then there's K3S, a lightweight full Kubernetes that comes in a single binary. This is one of the projects that Rancher Labs is working on, and we are really enthusiastic about being able to integrate with that. And finally, full Kubernetes. As I said, at the moment in the car, we are just up there, but we expect that going forward, those in-car computers become more and more like compute clusters, and we may use more of those technologies even in the car. Yeah, one way of looking at this is even if you don't need any of those scheduling features of Kubernetes and container engines, like starting and stopping containers on demand and spawning more if you need more of a certain type, just the virtual bill of materials of software that should be running in the car is so much easier if you can use technology like those text files, the YAML files that Kubernetes uses, or Helm charts, and then also configuration tools like Salt or Ansible. And we think that a lot of that will translate very nicely to car use cases. Yeah, this is a picture of how this whole ecosystem in the car could look like with a central compute cluster and those zonal ECUs. And think of those as potentially basically two different types of Kubernetes clusters. The central compute cluster is one, and then all those zonal ECUs are kind of a distributed cluster as well. Yeah, this is another picture that kind of shows how the architecture can look like. And there are more components, yeah, like you may want to add virtualization, KVM or Xen into the picture. There are also automotive-specific hypervisors or embedded-specific hypervisors, but we think that most of the stuff can be done on KVM. So for example, you could run a VM that is an Android infotainment system unchanged in such an environment, and consolidate existing hardware on a single cluster. And then most of the workloads would probably be workload containers, or as I'm calling them, containerized vehicle functions. And there can also be RTOS, real-time OSs, because as you'll see, for the full setup, Linux will not handle all the most safety critical features on its own from day one. So let's look a bit into this story, the certification story. This is what Electrobit is doing with us. We are talking about security, things like cybersecurity, this UN ECE VP 29. Then for the OEM, bringing the time to market down and so on. I've been talking about that. And finally, safety. And safety, if you are familiar with the automotive industry, there's the ASIL standards, ASIL A to D. We're currently expecting Linux to need at least ASIL B level. And then the total solution, let's say a self-driving autonomous car, of course, has a lot of ASIL D level features, but together with real-time OSs and cleverly combining the stack, we think the Linux will have to reach at least ASIL B. And there's a bit of a question: how can a Linux OS that hasn't been developed from scratch following SPICE or other safe development processes, but it's a community, how can this actually be certified according to, let's say, the Automotive ISO 26262? And the answer that Electrobit has found together with us is that we can look at the parent standard. So actually, ISO 26262 implements the IEC 61508, and there are provisions in that standard that allow to meet safety targets by other means. So basically, you can explain why things are safe, although they weren't developed according to the automotive standards. And that's what we're really doing here. There's a lot of complicated stuff involved in making this happen. But we are really confident together with Electrobit that next year or early 2022, we will see the first cars with safe Linux on the roads. At the moment, we are in the middle of shipping an Intel-based architecture to a first customer. So during the winter time, we'll have the first test cars with SUSE Linux in the car on the streets. And then these cars are collecting data for the second step, for the certification step. We are also working on an ARM architecture for other customers. And the goal is, as I said, showing compliance with an IEC 61508 under this section 3. The life cycle of those Linux distributions is an interesting problem that not everyone has solved. So SUSE has offerings for that. We have long-term service pack support, long-term support, even special deals for certain customers, so that we can support operating systems for, as I said, up to 18 or 20 years. So this is an example from our standard SUSE Linux Enterprise 15 offering. And we are working very closely with Electrobit to have to bring those long life cycles to the automotive industry, so that an automotive kernel doesn't have to be updated every couple of months or so with the latest. In many cases, people are just not updating it, but they will have to because of the cybersecurity regulations. One of the benefits of this new approach is that when you're using almost data center technology, you can also use almost common off-the-shelf hardware in the car. Of course, hardened for automotive use, but you can use standard Intel CPUs, ARM CPUs, and we'll expect a lot of the technology in the car to be more generic. So not so many special ECUs that can just do one thing, like, okay, I'm the airbag controller, I'm the camera controller, but just like in the data center, software that of course sometimes needs accelerator cards, so does most of the logic. And those software-defined functions, or as I've called them, containerized vehicle functions, also allow running the same software in a cloud, for example, or on a laptop in a test environment, as long as all your sensors and actuators also have a software implementation, that like a test case, a unit test. And I think that's really promising. You can do a lot of integration testing long before the final hardware is decided on and before the first test vehicles are on the road. Yeah, the virtualized test-driven development, that's really one of the core features here. Now let's summarize. First of all, we want to really bring Linux to the car, and not just for infotainment, but for all the layers of the software infrastructure in the car, from a central compute cluster to zonal ECUs. We are doing this together with Electrobit. As I said, the first pilot customer is going to have cars with SUSE Linux on the streets this fall. this winter. And then we expect these cars to collect data for the safety certification and so on. And we'll see hopefully a safety certified SUSE Linux or an Electrobit Corpus Linux in the next couple of months. And that's really a great step forward. But we will also go beyond that. We want to make sure that a lot of the technologies for container management that are being used in the data center, in telecommunication and so on, are translated into the car. One example that is kind of a blueprint is how the telecommunication industry really switched from shipping custom hardware to basically setting up standard servers and running all the compute functions, the network functions as virtual machines or later containers. And I think this can also translate nicely into the automotive industry. And finally, as I've mentioned before, this will mean that there's a convergence of technology from the car to the data centers to the clouds, allowing things like testing your stack in the cloud, or having engineers working on the exact same technologies when they build a feature for the car, let's say as part of the navigation system stack, and the backend where the data is hosted, and other backends that take care of user authentication, of making sure that the user really gets what he or she has bought. Yeah, unfortunately, we don't have the automotive white paper just ready yet, but we have a white paper on innovation at the edge that you can download at this URL. And that's basically the end of my presentation. We have now some time for the Q&A.
So, hi. There are some questions. First one. Okay. Do you intend to address infotainment as well, or only ADAS? So I think you answered that already. Or do you want to add
it's still
something?
A good question.
Yeah.
So the focus of this project together with Electrobit is certainly the ADAS functions, or in general, safety Linux. But ultimately, I don't see why we wouldn't do infotainment as well.
Okay. What differentiates SUSE from Yocto in embedded application?
Yeah, so I had this one slide where I explained how things work differently in open source in the enterprise. And I think that really translates to Yocto. Yocto makes it really easy to build things in the first place, and it's nice tooling for doing a pilot and prototype, but having to maintain a stack where you have those overlays and the BSPs coming from different vendors and so on, 10 years into the project, that's where the fun starts, or not so fun starts. And that's really where we think with our approach, we can help all the participants, all the vendors, and also other, I mean, third-party software suppliers who contribute to those stacks. In many cases, there are like dozens of players to integrate, because integration can be in parallel, not one after the other. Like we ship it to Electrobit, Electrobit ships it to the end user, and then they integrate with other components and so on. But we can do this in parallel. We have a CI/CD approach for the car, basically.
Okay. Can you stop screen sharing, please, Joe?
Sure.
Our faces are bigger on the screen. So the next question is, do you expect OS upgrade through OTA during lifetime of the car? And if yes, how frequent do you think this OTA will be?
Definitely yes. For the first customer, I'd expect this to happen every couple of months maximum. But of course, the ultimate goal is to have updates at the same speed as the guys from California that everyone is looking at. This may, in many cases, not be a full OS upgrade, but just features as containers. Yeah, you don't have to always upgrade the platform. But ultimately, yeah, it should be possible within. So one of the customers we are working with expects full updates of the car, including microcontrollers, in half an hour every whatever. I mean, however, how often they need it. So overnight, for example, that's the goal.
Okay. So next question is, we are using muslib on some of our prototypes. Is there a plan to support this in SUSE?
If you need it, yes, of course. The current footprint that we have is using plain glibc full size if you want, but yeah, especially in the container, yeah, you can have musl in the container, no problem at all. And for the OS, we are always working with customers on the necessary specs. Yeah.
Okay, next question. What is the value add of SUSE intends to bring compared to AGL?
Yeah, as I've said, for now we are really focusing on those safe Linux scenarios, and that's not what AGL was built for. It's more of an entertainment story. Of course, or infotainment story. It's evolving, but we are not working against AGL or other projects like Genevi or of course Electrobit is a major contributor to ELISA, for example. So it's not an either or, but we're just adding the traditional enterprise distribution side to things. So we built the basis very differently from how Yocto is built, for example. But then what's going on in your containers, for example, can be plain AGL code.
Okay. Then there is a question on QNX. It says, how do you view SUSE differentiator compared to QNX?
Yeah, we think that in the long run, the Linux approach is just much more agile. QNX has done a great job over many years in the embedded market, obviously. But when you look behind the scenes, in many cases, for example, yeah, there's a certification for whatever security level, but what you get is not the full Linux ecosystem, but very narrow focused feature sets. And people will need more of what Linux can offer and open source can offer. For machine learning, for neural networks, all the traffic sign detection, road detection, and so on in the ADAS space. There's so much software that will just not run as efficiently on QNX, or you basically are only getting very small, a very thin layer of the stack that you are working on. And if you're already using 80% open source, why not just go all the way and use the full Linux stack for that?
Mm-hmm. So next question is something, I think, a clarification. Does SUSE deliver full-blown OS, or just certain functionality, or the kernel?
It really depends. So in this partnership with Electrobit, our focus is, of course, on the kernel and glibc. We are not delivering, let's say, an adaptive AutoSAR stack at this point. Going forward, I think this will change, because we think adaptive AutoSAR can be replaced by more generic, like Kubernetes or Podman frameworks, even in the car. And then that's where a lot more SUSE stack comes into play. Yeah. But what those customers get from us is also access to the complete SUSE Linux Enterprise package set. So they can then, within their containers or in their own custom images, take any package they want. Like if they want a DHCP server, if they want, I don't know, CAN bus drivers, so they can get whatever we have packaged and integrate it. And we also deliver them the tool chain. So what we are using to build our own installation images and so on. This is also at Electrobit and at the customer side And basically, when we do a new check-in, we can roll it down to the end user, and they can then participate and use the latest updates that we've shipped.
So another Q&A. Another kernel compatibility thing is, apart from AMD, ARM, Intel, do you support MIPS?
We have no plans for MIPS at this point. What we are looking into is RISC-V in the long run. Yeah, but at the moment, it's mostly ARM. Let's say the NXP S32G platform, and others like Renesas or so.
Mm-hmm.
But there is Linux for MIPS, so we could pick this up if there's market demand.
Okay. And then there is one last question, which is about, I think, the economic aspects, and how do you expect OTA upgrades to be paid for, by user or tier one or through OEM?
I guess that's a question that ultimately the OEMs have to answer. We can imagine as a stretch goal that people would get OS updates directly from SUSE's update ecosystem in the car, but I don't expect this to happen anytime soon. So it will be, you have your whatever car from vendor X, and they come with a plan for over-the-air updates via a certain 4G or 5G plan, or Wi-Fi at home or so. Yeah, I guess that's mostly going to be between the car manufacturer and the customer.
Okay. And then there is also a person who says, really nice talk and Q&A, and thanks a lot. And I think now we're through all the Q&A questions. Thank you, Joe. And
thank you, Stefan.
I hope to see you soon. By the way, SUSE, my first Linux.
Great. Hopefully not your last. Okay.
Nope. Okay.
Thanks for having me.
You're welcome.
Bye.
And for everybody else, we see you right after the break. In 2 minutes with Daniel and Hermann. So we are back here with model-based systems engineering in an agile product development process together with Daniel and Hermann. And I will now mute my camera and microphone and leave the stage to you.
Hi, I'm Daniel Siegel from Lieber, and today we want to give you an introduction on model-based systems engineering and with a special focus on agile product line development. I have the honor today to have Hermann from Volkswagen join me on this presentation, and he will give you an industry context of why we need this. So Lieber, the company I work for, is an Austrian-based company with a subsidiary in the US, and we service customers all around the world, mainly in the automotive industry, but also aerospace, defense, medical, and all of that. So now it's up to Hermann to introduce himself.
Good afternoon. My name is Hermann Golbitzer. And when I was starting my job on Siemens, it was in 1985. We had a very well-defined working process and a well-defined working flow. Okay, it was without computers and tools, but it was very successful because we had an end-to-end method. Later, computers and tools raised, and also I was very deeply involved in hardware software code development and simulation. And that's why, let me say, I learned there a lot that how important systems engineering and model-based driven systems engineering is for a company.
Okay, thanks, Hermann. And currently, Hermann works for Volkswagen and helps Volkswagen to improve their systems engineering practices.
Yeah.
I'm Daniel Siegel. I was raised being an enterprise mobility guy. So I developed software for parcel delivery devices. And somehow I got into engineering tools. And my focus has been for the last 15 years to develop solutions around existing modeling tools. And I'm also heavily involved in industry and standards organizations to help drive modeling and especially the systems engineering side of the modeling forward. Just to name a few of the organization, I'm involved in Inkose and their German chapter. I participate in the OMG standardization processes, and I'm currently co-chair in a working group at the ProStep IWIP, which is an automotive standardization body in Germany. So systems engineering typically targets people that build safety-relevant cyber-physical systems, as the scientific would say, and that's typically everything from door openers, window openers, to cars, jets, and so on. So even the Department of Defense cares about safety-critical software and the norms that are affected. Some of the references of companies we have the pleasure to serve is, for example, Volkswagen. That's why Hermann joined us, but also Continental, Schaeffler, Bosch, Siemens, and also some Japanese like Subaru or Daihatsu. Okay. And on the other side, we also have people in the defense community that rely on our services and tools that we develop. For example, General Electric Aviation, or Deal Defense in Germany. So the things we tell you is not stuff that nobody uses, but it's not yet the application is currently not perfect in all of the companies around the world. And so there is still a big drive forward to improve model-based systems engineering. So now it's up to Hermann to explain to you the context in an OEM or systems engineering.
On Volkswagen side, now we are in the phase to use systems engineering on the complete Volkswagen enterprise. Also Porsche, Audi, Seat, Crafters. And we came to the conclusion that methods and model-based systems engineering will be the basic or the backbone of development and also for a complete company. So this means in an organization or in an enterprise like Volkswagen, it's very big. So you have car development, you have infotainment development, you have cloud and online functionalities, and you have a lot of different requirements, and you have requirements for safety, for test, simulation, configuration, version, variants. You have to fulfill also innovations and so on. So it's a very complex stuff, and we see now, and we came to the conclusion that also there must be a very deep and harmonized organization between the company organization, the system architecture, and also it must be well aligned to processes, methods, and also the tooling in a company. And this was a very long way to convince all the people and also the guys from the finance department that how important it is also to fulfill the future and also to fulfill now the production of cars. Yes, we should go to the next slide, and then this slide I will show you just how it should work together in an agile enterprise. So on the top you will have the process, the development process. In the middle, this is the method, and the method defines all the contents and the working style and everything. They are defined, and in the realization you can use different tools, implementation tools, modeling tools, and so on. And the very highest goal of this is also to fulfill costs, time, and quality, and to fulfill the enterprise roadmap and all the business models, and the last not least, to have a high quality in cars and the functionality in the cars. Yeah, the next slide, please. And here I will give you a small introduction how we have done it in the methodology. So here you have the example in the architecture of a speed indicator. And so you will have on the left side customer requirements, rules, regulations, functional requirements, and also non-functional requirements. And from these requirements, you make the functional analysis, and you came also to that you have to determine data, you have to determine speed, and you have to display the data and the speed. So you came to the logical system. This means also that you have a speed determine system and a speed displaying system. And after then, from this functional analysis part, you came direct to the technical development. And in the technical development, you can choose now if you will show the speed in a digital way, in a mechanical way, or also in an analog style. And also what the goal is here, you see that also you have fulfilled the SPICE and also the quality requirements. So it is the traceability is fulfilled. And if you're using model-based systems engineering with this method, you have just all the processes included in your method. You have not to care extra that you have all the SPICE requirements and stuff like this fulfilled. Okay, let's go to the next. And here you see what we have also seen on the Volkswagen side. So the software was increased dramatically. And the problem is when you're not care for the first day that you have, and this is very important to say from the beginning on the first day, if you will not care for the architecture, so you losing the corridor for the good architecture, and the architecture starts to erodate. So and the result will be that you have to investigate a lot of time and costs to came to the production, that you have also at the end the quality. You have a lot of testings and a lot of problems to fulfill, and also the next effort you have to do is to come back to the good architecture corridor. You have a lot of effort also to do for refactoring. And last not least, this is a problem you will have, that also your innovation products will come to a later phase. This is a problem. And also, if you add some maintenance or expansions on your software, so you have also to investigate a renovation phase in your software architecture. In technically, we say this is continuous integration and continuous delivery. You will fulfill all this. Yeah, and now we will switch to the technical part, how we have fulfilled this challenge.
And it's back to me. I have this slide just to bring the awareness again, why people invest in model-based systems engineering. For one, it's typical stuff. It's not a big surprise. Maybe a surprise for some might be that it's regulatory norms. So there is really laws coming from UNECE for autonomous and automated driving, for example, that really state in the norm or in the recommendation that you need to use systems engineering for the V&V of autonomous or automated driving. Growing complexity, I think, is a no-brainer. And below there is typical industries for model-based systems engineering, but there is many more that tackle these challenges today. So how did people do systems engineering in the past? And the past, I mean, 5 to 7 years ago, some still work like that. They had a very document-centric approach, which means all the various engineers created documents, they've been used, and new versions have been issued, and you end up with a pile of documents that is very hard to manage, and it's very hard to be sure, for example, for the test people, that they are looking at the right requirements or at the right safety analysis. And so this is really a pain in the back, and there is plenty of papers around this topic that it's very, very hard to survive the safety critical challenges of today if you do a document-centric approach. And a quick outlook. This is, for example, what the ISO 26222, the safety critical norm for automotive, requires from your development process. As you can see, there is many views and many types of documentation and work products you need to deliver. And it's really hard if you all have them in Word or Excel or PowerPoint. And this is not uncommon, don't get me wrong, but it's really hard to maintain them and make sure that they stay consistent during the product's life cycle. So, for example, technical safety requirements is one of these work products you need to deliver. And additionally, you have the relationships in the supply chain also involved. And at the end of the day, the OEM will have the trouble if an automated driving car does something stupid. But obviously, there have been many suppliers involved in developing such functionality in the typical case as we have in the German automotive industry. So typically there is 3 solution strategies that are applied to tackle those challenges. One is that you introduce model-based systems engineering. On the other hand, to be able to satisfy the norms, you will also have to introduce a clever configuration and change management. So it all sounds very strict and very big V model style. But on the other hand, to be able to fulfill today's challenges in terms of time to market and growing complexity, you also need to work in an agile style. And this is a real challenge to combine these 3 solution strategies to be successful. Modeling. I know that in the software development community, many people say, oh, UML, SUSE is all dead. We learn it at university and it doesn't make sense. Revisit it, it makes sense. And you are all using modeling to some extent. Maybe it's not called modeling, but you're using some data access layers and you build models to use them. In this specific case for safety critical systems, I know a guessing game is not obvious to be safety critical, but still it's a nice example. What you do, you bring your requirements into the model and create trace links or fulfilled links between your class diagrams, block diagrams, state machines, activity diagrams. So this is already an important step, that we do not just model static architecture like in typical software design, but also core behavior is described in the model to be able to do all the analysis that are required to build safety critical systems in a successful fashion. And what happens behind the scenes when we create those links is that we create a graph. So it's a network of data, and this network of data is the intelligence that the model has. It's not about diagrams. The truth of the model is always the graph behind it. And this is very interesting, that the diagrams are views on the model. So they are for human readability. But don't forget, you also build models to have the data available in a machine readable format, where obviously a diagram view doesn't make a lot of sense. So you always have to have all the information in the model, and the diagrams are just views on the data that make the data accessible for the specific roles. And this is really important point. You know, if you create activity diagrams with PowerPoint, you draw. If you build activity diagrams with a proper modeling tool, you create the model behind the scenes that can be viewed from different angles or even read by a machine, for example, to generate code. And again, this is an example of the two types of modeling that typically occur in model-based systems engineering. On the left, you see a block diagram, which is basically a class diagram specific to build the architecture of cyber physical systems. You can, for example, see a brake subsystem and a power subsystem. They both have relationships and interfaces to the brake pedal. And on the other hand, you can see an activity or a behavior for the accelerate operation defined as an activity diagram. And this is the types of models that are built in today's model-based systems engineering practices. And always in relationship with requirements, with trace links, so you know why you build stuff, and if the requirement changes, you can find out what types of the model or functionality in your system you probably need to revisit to validate if the changed requirement is still fulfilled. This is like the summary. I think you have to think of a model as something in the repository that you can use to generate work products like documents. You can access it with tools, or you have processes that create the model or use parts of the model. There's a very simple thing about modeling. If only your team uses the model, you are on the wrong track. If you introduce modeling into your company, you always need to make sure that as many people as possible can benefit from the model you engineered. Our preferred tool when it comes to modeling is Enterprise Architect from Spark System. It's not super, it's pretty affordable and very flexible, and you can use it for various types of modeling. Again, this is the example I showed you before as well. This is the activity diagram of the accelerate operation shown in Enterprise Architect. As you can see, typically those models are structured in trees, but again, this tree is only one view on the model. There could be a different tree for a different purpose, but logically you structure your model into packages in a tree. From the good old UML days, this was typically like the package namespace from Java, but this is not relevant anymore. You use the tree mainly to organize the work and to have a nice way how you can access the model and work with it. And now comes the interesting things. Those graphs are pretty hard to do the version control because you need clever diff and merge tools in order to do optimistic version control. And when you look at what customers want to do when they go agile, they need to learn from the software people and use processes like Git flow also for their systems engineering models. So you can use feature branches also with your models. This enables you to roll forward changes to the product in a much more controlled fashion and in a very granular way. So the benefits that the software processes around Git had now are also used in the MBSE space. And this is what we enable with our technology that we will look into a little bit later. Again, back to norms. I know I talk a lot about norms, but I just want to show you an excerpt from the IEC 61508, which is the base norm below many of the safety critical norms, that there is clear statements in the norm that you have to have effective measures of version control and change management, that you need revision index, and so on. So it doesn't help if you have your models lying on hard disks. You are not fulfilling the norms and are not working state of the art. In order to do so, you really need to make sure that the models are also under version control as all other development artifacts are. And this is another example why branching makes sense. It's very hard for variability if you have to maintain a 150% model. Models are complex anyway, and if you have to build a model that contains all your variants, it can be pretty cumbersome and hard to interpret by users. So what you can do now with the technology around Git, you can also have the variability in the version control system using branches. The example I show here is we have a platform trunk and a platform release branch, and we can branch out to customer projects, do the changes, and bring back only the stuff we want to the platform. This way we have a very controlled process. The project models stay very consistent, and it's much easier to control than if you have one model that contains the platform plus all customer projects. It gets very hard to maintain. You get into trouble if you want to keep, for example, the customer on an older version of the platform and the next customer already is on a newer version of the platform. If you want to do all of that in one model, you get into trouble very, very soon. So for all of these nice things with merging, with branching and so on, three-way diff and merge of these graphs of the models is a key technology, because with pessimistic version control, you can't do anything remotely called agile. So we need optimistic version control, like it's normal in the software engineering world for quite a while now. And this means we need merging capabilities on the model. In this case, Philip took longer to change the model than I did. And so when he brings it back into the version control, there will be a conflict. And this conflict needs to be resolved. But the data in the file is stored as a serialized graph. So in order to merge it properly, you need to have a different merge tool that understands the graph and can do a logical model aware diff. With WinMerge or Beyond Compare, it's simply not possible to complete such a task. Also, you need strong diff capabilities for reviews, which are very common and day-to-day work in all of the safety critical MBSE tasks. And obviously it can occur that the review takes longer and you need to merge back things found during the review in a newer version and so on. And again, you will have conflicts, which is not necessarily a bad thing, but you need tool support to be able to manage those. So the goals for branching in model-based systems engineering, or MBSE. It is on one hand to enhance the modeling process to be more agile and more similar to the software way of doing configuration management. And on the other hand, you want to make sure you can do long-term parallel development of versions and variants. And obviously, if you have to deal with audits and so on, it helps if you can base your work on existing processes or workflows like Git flow or other feature branch-based product development workflows. And the business driver very often is to provide support for the functional safety critical norms. So in our case, we also have a certification toolkit for ISO 26222. But as you can see in the image, there is many norms and they basically all have the master norm, this IEC 61508. This is an example how our diff and merge tool for models look like. It's very similar to WinMerge or Beyond Compare, but as you can see again, it can read this tree. In modeling, we call it containment tree most of the time because it's just one view, so it's containment tree. And we also can see differences on a diagram level and even have visual diagram merge enabled. And in the lower pane, you can see details of what has been changed. On the left, you can see all diagrams that have been changed and all elements that have been changed on the top view. So again, the trick about this diff and merge user interface is that it enables you to understand the model while you have to do the task to verify or merge the changes that happen to the model. So Hermann, do you have some more points from your industry experience for the conclusion?
Yeah, I think the main goal we have fulfilled with Liebe was that we can. It was very successful to adapt and to adapt model-based systems engineering on the Volkswagen environment, because Volkswagen is a big company with different brands, very different cars. Let me say old cars. So we will have some cars, they have not the innovation, everything inside, but they must also have a lot of modern elements like online versions and stuff like this. And as you know, we are on the beginning to have also a lot of electric cars with a lot more functionality inside, and all this is was possible to integrate it with this version and variant controlling. This was the main breakthrough for model-based systems engineering here on Volkswagen side.
So I take the conclusion now to my side. So our idea is always and has always been to reuse established workflows from software engineering for the model-based systems engineering, and to enable agile team collaboration based on branching mechanisms of the version control systems. This allows you to give you a consistent development state because you have precise versioning. And on the other hand, the branching has one big benefit. If everybody is working in the live model, it becomes very, very complicated and cumbersome to review changes they did to the model. If you work with branches, it's very easy because whenever there is a merge from one branch to the main branch, you have a perfect trigger to review the work that has been done, make sure it is in line with your company rules, it is in line with the safety goals and so on. So this is really interesting to have this really the change in the process somehow happened with the capabilities of the solution, but it has proven to be very successful in the industry. The outlook, and I think this is also very interesting, that we already have customers that they make merge requests for models in GitLab or GitHub, and that we see a trend that they try to do automatic merges on build servers. And so the trend also is going further with applying stuff that worked for the software industry, for the software processes, to the modeling. Continuous integration and DevOps for models is something we see on the horizon, and that will be the next thing that we see. Also, on the other hand, currently we are working to build something like Maven or NuGet for models, where you can have reusable model components that can be distributed in the organization. So you can see that there is a strong context where the modeling people really try to learn from the software engineering and apply this to build better safety critical systems in the future.
And what was also a big advantage of this was also that we have so many people involved in one project. There are thousands of developers, a lot of different companies. They are customer to us, and also different countries. And so with this handling of the models in Git, and also for this variant controlling, we have to do it also in parallel with the software development. And now we was able also to have also for a very distributed and a lot of involved people and developers, and also management and project leading. So we are reached the goal not to lose the overview of our products, our software, and our functionalities. This was the main goal we fulfilled with this method.
Okay, thank you for your patience. We have been on a fast track today. We've been fast, so we have more time to take questions, should there be any.
Yeah, we're good in time.
So, I'm back, and let's have a look at questions. First of all, thank you, Hermann. Thank you, Daniel. Was very interesting. And I'm not the only one. There's also Anonymous who says, thanks for the amazing talk. And the next, first actual question is, what was the impact of versioning on the workload for the team?
Hermann, I think this is a question for you.
Yeah.
The versioning, we also practice this in the software side. And now we do it parallel also for development. And at the moment, one people is doing all the versioning for our infotainment part. So it's not really a big workload you have. The biggest workload we had before was, so we was not clear what are really the differences in the different variants we have to handle. And we found it out at the end when we was testing direct in the cars. And also after then, this was a lot more effort to find it out via emails and PowerPoints and Excel sheets and phones and a lot of meetings to find the control, or to come back to the control and all to fulfill the different variants in the cars. Because we have also deliveries cars in America, in China, and so we have, for every country, you have different variants in the same car. Like in the Golf 8 now, number 8, if we deliver it to America, we have other rules and have other also functionalities. And this was very hard to have the control at the moment. We have an overview of this. So the workload was decreasing dramatically.
I can imagine that the workload is distributing also along the process and not jumping up at the end.
Yeah.
And I would say after you learn the new trade, generally it's less work and much less chaos.
Can you imagine this? Okay. Have you considered using the Arcadia method from Thales and Capella tool? Both are much easier to understand and better suited for MBSE compared to SysML UML.
No, we have done it not.
My take as somebody involved in automotive standardization groups also is that they generally prefer to stay on the SysML boat because there is more tools, not just one tool, and there is a huge standardization body behind it, and it's easier than to use a specific thing from one company. If your ecosystem is built with many suppliers, many OEMs, it helps to have a common language.
The problem is also it was not the goal to use maybe the best tool ever you can have in the world. The goal is that we find to have a common basic for development and a common method how to work, and for all the customers and all the developers. There must be, the goal is to find a common understanding for the job you have to do, and not to use the best tool or a special method. This is not enough. It's just one part. It could be a good solution if you make for prototyping. So maybe it's better to use it there. It could be possible because you will be faster or something, stuff like this. But for product generation, version control, and all what you have to do in a big company, it was not used now. Maybe in the future, we will see.
Okay. So last question. So this was the last question, but I have one more question for you, because you said at the very end that you're also looking forward to DevOps and continuous integration stuff. What would be the greatest problem in this context? This is compliance, security, or simply that people do not or are not there yet to also trust these methods?
I think it's trust, and it has to grow on people. We have people that already use GitLab for their models, which is already a very good start. But it will take a little bit more time for people to look into this. But we can clearly see from the inquiries and from our experienced customers that they are moving in these directions.
Okay. So thank you for that talk. It was very informative. And it also seems to be kind of a trend of things we see in our talks. We had in the last live week something about architecture decision records, which was more or less similar to what you told, but on a much smaller scale. So thank you again for the talk. And for all the people in the audience, it's time to grab a coffee, and we will be back in about a quarter of an hour for the panel on will the mobility industry tilt towards infrastructure. And there you will see one of the two speakers here again. It's Daniel, so I don't make a secret of it. And see you then.
Okay, bye-bye.
Thank you.
Bye-bye.
Bye-bye.
Bye. Hello again. I hope you grabbed your coffee. We will soon join Jana Neikova, Michael Hirschbichler, Sergei Sergeyev, Michael Zweck und Daniel Siegel on stage because they will discuss about the mobility industry and if it will tilt towards infrastructure. Let's see where the discussion goes. And now let's head over to Jana. Hi, Jana.
Hi all.
Hi.
Today's discussion, as already Stefan mentioned, will be under the topic about will the mobility industry tilt towards infrastructure. First of all, I want to introduce all the people who attend the panel today. We start with Daniel Siegel. He's involved in model-based engineering since for the past 20 years. And he has gained deep expertise handling critical software projects around the world in the IT and footwear industries. The second panelist is Michael Zweck, who is a senior pre-development engineer. He has initiated a pre-developed project 9 years ago about traffic light information and has gained quite good expertise into the area about mobility. We have also Michael Hirschbichler here. He has studied computer sciences at the Vienna University, and he's currently engaged in developing one of the largest charging networks in Austria. We have also Sergei Sergeyev, who is in the field of data science and IoT for the past 10 years. And he has the most expertise in retail and e-commerce. And we can start. All of them will discuss over the topic and provide you with more details relating the mobility industry. Guys, first question is, what is your opinion about the impact on the infrastructure? Lately, it's been quite hot topic with very different opinions we have heard, but how does it impact the standard understanding of the infrastructure? Sergey?
Okay, so yeah, thank you. Thank you, Anna. About the infrastructure in terms of mobility, I mean, probably Michael, yeah, both Michaels, they have more expertise in that direction. Probably something which I'm seeing is that the future with the autonomous driving, it will become and it will be very popular topic. So so I would just put some notes and then we will jump one on another. So here what I see that for autonomous driving, what I read about 40% of the roads in US, they meet requirements of good ride. So it means that even in US, the roads the infrastructure on the roads level needs to be improved. So this can be one of the autonomous part about the roads. So now I will just give to someone else, and yeah, then the topic will evolve. Yeah.
I think because Sergey mentioned autonomous driving, I think it's also a discussion if somebody wants to build infrastructure that makes it simpler and safer to develop autonomous or automated driving. If you put sensors in the roads, it would be much easier to develop an autonomous car than if there is nothing and you have to drive on black tarmac and orient yourself with lines and side markers. You know, even if the side markers are gone, Can you still drive automated? Who knows? I have some experience with Nissan products, and I know once the line is gone on the side of the road, there is no support anymore for autonomous or partly autonomous steering. It's gone. So only on a proper road, the car can drive reasonably well. So that's my personal experience. From an engineering side, we can tackle it later.
My thinking about that is this is one of the great questions regarding autonomous driving. Do we really need additional infrastructure on the street, like a good quality road marking or communicating traffic lights? And if you think about the activities from the big developers of automated driving, they usually don't talk about, okay, we are waiting for some specific communication stack or something like that. So they usually expect that they are able to drive without additional infrastructure installed. But there, I think the complex things are starting. So if you want to cross an intersection with a traffic light, usually you get two different physical informations about the, or you have two sensors to get two different physical informations if there is maybe the crossing blocked or something like that. But what are you doing with traffic lights? So usually you have an image processing to know that the traffic light could be red or green, but what is the additional one? I think that we need additional communication stack between, as an example, traffic lights and the car to be safe and have two different physical inputs regarding that, as an example.
I have a good point that might lead very well to the second, Michael. And the energy question is always a topic, you know. The less infrastructure, the less clever the road is, the more computing power I will need to drive on it automatically. So I will burn more energy. And this is a perfect handover for Michael, I guess.
This is really perfect. Yeah, thank you. Well, the energy consumption of a car, the main part is the driving itself. So it doesn't matter if you have a large or small computer. I think it does not weigh that much. Well, we had one Tesla driver. I know of one Tesla driver who had a blockchain. Who was calculating blockchain in the franc. A Bitcoin, sorry. From the infrastructure perspective, you have to think about the not just the street, but also the charging facilities. So if you're driving fully autonomously, then there's a question about how can I charge fully autonomously? Because a self-driving car doesn't need a driver inside. We have car sharing. We have autonomous cars driving without a driver to the destination where it picks up the designated driver. So we will come to inductive charging probably. And so the energy consumption of the whole mobility or e-mobility, we will need much less energy per kilometer than with a diesel or hydrogen driving. So about 700, 800 watt hours per kilometer on diesel compared to 100, 200 watt hours per kilometer on electric driving. So the consumption per kilometer is going down. It's just another medium. On one side, it's diesel. On the other side, it's electricity. So the whole energy consumption will reduce with the switch to e-mobility.
Michael, thank you. I have one question which is most valid, I think, to both Michaels. Here, you mentioned several times about energy, autonomous cars, etc. But do you think that world is ready to pay the cost about that? Because it would not only impact the energy industry, but also would impact people's minds, a lot of engineering behind, a lot of connected devices, etc. Do you think that we are ready about the cost? And what is the cost?
The costs of the charging infrastructure, or which cost do you mean specifically? Or
Cost in terms of efforts, in terms of what additionally would be needed to build this and to make this available for use.
I think the e-mobility will change at least two industries completely. On the hand side, the Michael Zwick's industry with the Audi, and on the other side, we as a utility. Imagine, let's say in 2025, you drive with your electric cars to your company, you're charging there, the car is charged using the photovoltaics of the company. You drive back to home, you plug in your car at home, and with bidirectional, that's okay, I got it. Bidirectional charging, you charge your home, or you give energy to your home where you can cook or activate your sauna and so on. So we will sell less energy in future, and the grids, which are the backbone for the energy distribution, are used quite a lot, and this is quite a test or a stress test for the grids. So on these costs, the copper or the aluminium you have to dig into the ground, these costs are quite high.
If I can jump here, because I mean, looking into the broader scope or broader view of this topic, what I see that we all know with the American election what happens, but also if we are talking about global climate change, we know that the Paris Agreement, US will join. There is a plan to join again. So what I'm thinking that with this this unity, I mean, this effort which the countries are doing toward climate change, we will go to toward electrical or autonomous driving or toward that direction. So there will be a lot of regulations, and we all know in EU what's happening. So what I'm seeing in the next 10 or 15 years, it will be like what it happens for couple of months during the coronavirus and all digitalization. So my feeling is that this sector will evolve and soon some advancement will be done in the area of progressing in that direction, and because of the humanity at the end. I mean, there is a urge. So yeah, just to give a different perspective.
Thank you, Sergey.
Mm-hmm. So I think the impact and the advantages we will see will be huge, and like Sergey mentioned, the environmental footprint we need to or regulations must control that. So if you think automated driving is a common technology that's used by everybody, so we researched that sometimes in special situations, maybe people who would not drive a car use these individual mobility more often because they don't need a driver license and they want to go to their skiing area, and they sleep in the car, and there could be much more movement besides the effect from the coronavirus. We are now used to home office, but for leisure times, there could be more movement, or pensioners who have been retired, and they are now much more likely to travel around the world or around their city or something like that. So there is movement in both directions.
And I think that it's really important, and back to the infrastructure, that it will work, you know. The current solutions that immediately switch off if the road condition is not nice, this will not be the way into automated driving, because if I jump in a car, automated driving, I expect at least that it drives for 100 kilometers without disturbing me. And this is a difficult task with all construction works and so on. And this is where we have interfaces with infrastructure. If the roads are not maintained well or not it's not taken into account to be ready for automated driving, it will be a very hard job and a long road to this personal train style automated driving, where you can really sleep or work or whatever.
Yep. I do agree that the lots of pros that we see with autonomous driving comes with a lot of work and quite big impact on all industries. But do we what do you think that it would be the right approach? Because behind all the changes and all the logic in those autonomous cars, there will be a lot of data that would be stored somewhere, or quite heavy and big algorithms. Should we rely into storing the data into one hub, or to use more hubs for different parts of it? What do you think?
So probably I can start with that. There are two directions. If we talk about infrastructure, because we know that if the infrastructure is not so developed, one of the approaches is if we can make a more precise mapping of the roads. So this is one direction, which is, if the infrastructure is not so developed, we need to spend time on mapping, improve that mapping, which is one part. The other part is with the sensors. We know that now the most expensive part of the autonomous car is the radar, which is on the top of it. It's long distance radar, and normally it costs. I think there was a presentation. It depends, between 100,000 euros. So this makes very expensive, but also it generates a lot of data. So what I can split that now we need to have very powerful processors which are working on the device level, which needs to have fast interaction. Should they stop? Should they steer? Should they go left or right? Turn left or right? And also some of the data need to be transferred via different communication channel, which can help for the communication car to car or car to infrastructure. So to know where that place would be. So this is what I see. Yeah, if someone else have something to add.
Well, I think that the storing these car data is very relevant to the platform that is used by the group of cars, maybe spread it over various of OEMs. For us, it's very critical to get the data. So at the moment, we are thinking for infrastructure. We have if we want to connect some traffic lights, and with the traffic light information, we connected over 30,000 traffic lights in the US, and the problem is always that there is usually a weak standardization regarding these infrastructure data. So in every region, they start to develop, and the responsibilities are not over a whole group of traffic lights or something like that. So if you reach a city, there are some traffic lights controlled by the state, and some traffic lights are controlled by the city, and this is similar to the worldwide, what we see worldwide. This is nothing that is at the moment in common. So we're not having problems at the moment storing the data. It's more processing the data, getting the data, because we need different data contracts, the data licenses, etc. So this is one thing we want to emphasize. So we want to work on standards. We want to work on data, global data licenses, so that a city knows how they are able to provide the data, and in what format, as an example. And these data must be processed on a state level or on a country level. And there are activities in Europe, and or as an example, there is a lot of activities in Holland where they put a statewide data center in place where all the government agencies send their data towards, and all new connected infrastructure is providing data to that data center, and people can make a license for that and work with that data. And this is one very important step, and we are far from getting everything digitalized and so on.
Thank you. Before we continue, I just want to remind that we have an open session in Slido where all of you can join and ask your questions if you have any. I see that we started having some activity there. And as a follow-up of Michael's words, Michael, I think that this leads to quite big complexity of the algorithms, as I mentioned earlier. And here we can touch a little bit the topic about decentralization in order to reduce the complexity. So can you share your opinions here?
Yeah, I think it's really a question how much you invest in infrastructure to make problems simpler. It can be, on one hand, if we think again about the road with sensors embedded in the road communicating to the car, it can stop innovation to some extent, but it will make it much easier and faster to have automated driving a reality. But on the other hand, if those sensors are crap and they are deployed in 28 countries in Europe, it will not be possible to update those sensors in a timely fashion. And who owns the information that this data creates? On the other hand, a bad example, I think, is charging infrastructure. From my personal experience, because again, Nissan driving can be really challenged. If there is only the Volkswagen plug, you are stuck. And if you look at the US, which is pretty interesting, it's easy to go coast to coast with a Tesla. It's virtually impossible to take an EV, a Nissan Leaf, coast to coast, because nobody took the hassle to invest in the charging infrastructure to go across Montana. With a Tesla, it's possible because it was a priority for Tesla to also create the infrastructure to make their product usable. And they created a big barrier for European EVs or Japanese like Nissan EVs, because nobody took the gamble to invest strategically into charging infrastructure that would enable you to drive cross country in style. And this is a very good example how private investment in infrastructure can be a problem. On the other hand, it can also, if government builds infrastructure, it can stop innovation. I'm not sure where the reality is.
I take this chance to give some information from my job as a judgment operator. We know the problem, we know the issues. Driving a CHAdeMO operated car is quite tricky now and in future. We have in Europe we have two platforms at least which enable roaming. And this roaming is not just a technical part, which is quite exciting for me as a technician, but it's as boring as it is, a tax part, it's a legal part, it's Eichrechtskompatibilität and so on. Eichrecht, I'm sorry for this German word, but that's German as it is. And we are working on interconnecting this infrastructure hard. We are opening our information. So I'm absolute fan for open data. We as a charge point operator want you, Daniel, to have the best possible information about the charging infrastructure. Is it free? Which kind of plug? Which charging power? Can you reserve it in advance, transparently maybe, and so on. So we're working on, I think open data here is a must next to traffic lights or something else, like Michael told before. We have to enter these data to the market to push the whole topic forward. So Daniel, I hope in 1-2 years it will get better.
Yeah, this with the open data, we all know that especially the data, I mean, if the data is gathered from the government, from the municipalities, we all know that it needs to be open. I mean, what I mean is that data scientists and people who work with data, with models, know this stuff. This is how the innovation goes. It doesn't matter. It's a open source society, open source code, open data. And something here which there is one question which I think probably it's good and it's relevant now to the topic: who is paying the expensive infrastructure, state or consumers? I mean, because if still continue to be the state, it makes sense to have open data, and which is one approach which needs to go through the policy decision makers to have standards from the European Union stuff, then probably US, because it's one of the most developed, and also China. So these are the main hubs, which is one of the approach. The other approach is like the big companies. It can grow up as a service which which can be a service. So it makes sense in the as Uber. We all know Uber, how changed the taxis service as a service. Probably in the next stage, this can be again a service. We can pay for someone to take me from that from point A to point B, and all the rest, like all the the car, the consumptions, the roads, probably can be maintained by them. But I think it's in the future. It's so yeah. I will love to hear and your opinions. Yeah.
Do you mean regarding that we have something like a platform that delivers good quality data and collects maybe charging information possibilities, like Uber collected information of available drivers and made them easy available and always reachable, like that?
Yeah, I'm just imagining that. Okay, so now let's imagine there is no roads, and who needs to take the responsibility? And if you are paying for a service, is that I mean, because you probably from Audi and from all this stuff have some visions or some ideas around that. I'll be love just here, because this can be one approach. It's totally driven by the innovation, as Daniel mentioned. And then the innovation company, probably it will be one of these big players. They need to make something. Or the other approach is by government. So yeah, just we know what is the current status now. It's the government driven. It's the municipalities and different consortiums. I mean, from countries. But do we think that the future can go in that direction, toward services?
Sure, but usually these kind of services, if they are not this easily interrupting, it's really a tough business to build this up. So if you think about charging, this is a huge invest, and you need areas to put the charging stations and so on. And I think there have been a lot of activities in the past. We have now the home charging box funding from the German government. People are investing themselves, industry is investing. So it's very interesting, but this is not something that it's easy made and easy decision to say, okay, now next year we have enough charging stations for all of us, especially if when we see that electric cars are built in these numbers. It will be really interesting how this is growing together. So I talked to the Norwegian Verkehrswesen. They explained us that it's much easier to make charging stations in Norway because they from a historical point of view, they had a power plug on every parking lot because they wanted to heat their cars in the during the winter. And if it's freezing cold and you get it to a supermarket, you usually have there already a plug where you can make your car warm and have. And so there was a basis infrastructure to use. And this is a totally different if you think about how you get the power. And I think Michael can explain us what the steps need to be taken to make power available for these huge numbers of cars we're getting.
Yeah, it's. I think the number of charging stations will grow with the market. Thanks again. Will grow with the market and the requirements, but we have some nice bottlenecks. So if you imagine you're driving to Croatia, for example, or to Greece by car, you have to pass the Autobahn in Austria or the Brenner Autobahn to Italy. So if you imagine you have holiday beginning in Baden-Württemberg, for example, that's bad. Bayern, for example, Bavaria, and all are driving down. You have thousands and thousands of cars which have to drive down. They create a peak. A seasonal peak. The whole year is not that much, and they want also to be able to charge. So we have to be prepared for the peaks. It's like mobile phones on Sylvester and New Year's Eve. So how can we cap these peaks? Do we have to cap them? And this is a question which is the high class. On the rest of the charging infrastructure, you have to be split into two parts. The one is the fast charging infrastructure, like Tesla does quite well with its superchargers, or Ionity does quite well. Here we have a lot of investments, and it's hard for us as a utility to invest this money, as the OEMs can say, okay, I take 10,000 euro by each sold car, for example, Tesla, and invested this into charging infrastructure. So I can earn a lot of money to put in the infrastructure, and they did it very well. And that's so on the fast charging and supercharging infrastructure, the OEMs have an advantage. The other part is the destination charging, hotels, companies, your households, and so on, your small wall boxes. And these are quite cheap. They can be load controlled in combination with the photovoltaics and so on. This is the easy part of the whole game, and these make the big numbers. Most of your drive, if you think back, the last time you drove your car, how many kilometers did you drive? 10 kilometers, 5 kilometers, 20 kilometers maybe. So one full battery lasts for 200 kilometers. You can drive 10 times to a company without charging, maybe. So this you can solve with your high number of destination chargers, which are quite cheap. So you have a balance of both. And the superchargers, one stall of such a high power charger costs about 100,000 euros with grid connection, with whole work, the infrastructure itself. And this, I think the OEMs could pay it. Don't you, Michael? Don't you think so, Michael?
Okay. So following your discussion, I have one question. Actually, somebody already wrote about it. While getting to fully autonomous driving or creating the whole infrastructure needed about that, do you foresee any future full of hybrids? People are giving examples about that, like hybrids between electricity cars and autonomous cars, or like we have nowadays with between electricity and gas or diesel, for example. It's, do you see something like more growing the number of hybrids?
No.
No, I think at the moment electric cars are the way to go and are expected.
Hybrids carry a lot of dead weight in both modes of operation. I think there is a future for high performance hybrids, where you add an electric drivetrain to accelerate 1 second faster from 0 to 100. There is projects out there that do that, but there is no main time future for the complexity of the current hybrid architecture, where you have a big engine and a small electric engine. I don't believe in that. In Austria, it's very attractive because you save a lot of taxes. In Austria, the tax for buying cars has a long time been based on CO2. And if you buy a Panamera hybrid, you pay 0% of this environmental tax. And if you buy a Panamera V6, you pay like 20 or 25% environmental tax when you buy the car. So in Austria, those high-end hybrids are fairly cheap compared to similar powerful cars, but this is just a tax thing, you know. It's not the reality.
Yeah, that's true. But I think the funding for electric cars will reduce when it's getting more mainstream. But on the other hand, the batteries are getting cheaper and cheaper. They're also so that this equalizes that or levels that out sooner or later, and then as soon as electric cars are mainstream, I think there will be also taxes, like today for a gas or for a hybrid car or something like that.
I fully agree with Daniel. The extra weight of an diesel motor is not worth of it. It's just for the time in between. We are afraid of having too less charging infrastructure or too less kilometers to drive electrical. But now these thoughts of the customers are gone. Everyone who drives electric car well in Europe knows there's a charging infrastructure reachable everywhere. It's not clear if you can activate it with your car or your app or whatsoever. We have to work on this, but it's reachable at least. So we are taking away these German Angst, these angstes from the customers. And well, it's working every day better. We have in Austria, I think, about 5,000 charging stations, a few hundred DC chargers and then a lot of AC chargers. So currently there are enough charging infrastructure. And when we as a charge point operator see that there is a peak or a lack of charging infrastructure, we see a business there. We will build it, or the OEMs will build it. So this goes in parallel. And well, back to the first question. I think hybrids are just the next 2 years. We don't talk about hybrids.
Bridge technology, but so I'm.
Yeah, exactly.
We just ordered the E up personally. I'm waiting for that, and we have a hybrid car, but we're also traveling on holidays with a trailer. So there's no way to do long distance traveling at the moment with the electric car with a trailer. But I think that is just a point of time, question of time.
And I think charging stations are a perfect example how new technologies are challenging for the not so adventurous. If you do a long distance trip in something else than a Tesla, you need to be ready for adventure. Because all sorts of things happen. For example, the charge plug is frozen. You have a free stall available, you plan your trip accordingly, you arrive, the charge plug was laying in snow, frozen, no way to charge. Or in summer, if you have a car that does not cool the battery, you find out that charging takes double the time in summer. And all of these things. So I think the charging infrastructure is a good example for a technology that is not yet ready for my grandpa. And this is and all this roaming stuff, you know, we travel a lot to automotive OEMs or suppliers. And if you go there with an electric car, it's always an adventure. Even if you go to their electric innovation center, it can happen that you cannot charge your car because you have the wrong plug or it's broken, whatever. So we happen to go to a major automotive supplier, to their electric car center of competence. And the only charging we found after talking a lot to people was 220 volts, which gets you maybe to the next charging station, but it was an adventure, you know. It's always adventure. If I travel long distance with the Leaf, I'm used to drive it down to 2%, not because I plan for 5 to 7% rest, but there always happens something that I need to go for an extra thing. And if you panic, you will give up immediately.
But Daniel, if you think about your experience, so we are talking about autonomous driving and putting sensors on the road so that autonomous cars are able to drive there. But we are not able to agree a payment method, and say, okay, every charging station needs to have these two conditions, so everybody who needs a charging is able to charge there.
As a user, you know, I'm playing the user now. As a user, I don't understand two things. Why can I not pay with my bloody credit card at every charging station? Not understandable for me. The second thing, when we talk about this partially autonomous driving that we have today, why does the car pretend to drive in traffic, but it decides in the glimpse of a second, I'm in charge again? You know, if you drive some Nissan, sorry, but all my modern car experience is related to Nissan products lately, not because I own them, but this is the fancy stuff I get to borrow. And when I drive with the Nissan in LA, it works perfectly to chill in traffic. You know, it's crazy there. You perfectly understand why you want a car that can follow other cars. But then suddenly the line on the right is gone. The car says, "Bim! I'm out of here." And this is also a usability problems. And if we can make infrastructure in a way that it helps overcome these usability challenges, acceptance of the new technologies will be much better.
Yeah, something what we mentioned about the infrastructure and the hybrid, probably we didn't touch because something which I'm expecting is the innovation in battery life and all this. There was a research for a battery which will last 10 times more, but the discovery was that there is a very rare element. So I think they stopped this research. So with the hybrid, probably the first thing was the hybrid because of the battery, because 100 kilometers, it doesn't make sense to take such kind of car, and now it expands. So what I will add here that once the battery start increasing their lifespan where you can travel, and also there was some ideas that battery can be a kind of infrastructure. So you just need stop, remove it, and take new one and continue further without wasting some time.
This is a very interesting point because, again, sorry, I'm really not a Renault guy, but I have to come back to Renault again. They did trials with exchangeable batteries, I think 20 years ago in Israel. And it didn't work out because we don't have it on the road. But Renault had a fleet of cars in Israel. It was 15 or 20 years ago, where they built robots and stations where you could exchange batteries. Even Tesla showed it on stage to exchange batteries. And for industrial applications, there is big, large batteries where the battery acid can be stored and like a tanking experience, you know. But again, none of these technologies, even those that have been trialed, have made it because it's obviously more complex in terms of infrastructure and cost than to solder batteries into a car.
Yeah, and also if they're doing this, it needs to have a standard, because it's easy to make it only for Tesla, but there are so many cars. So it just, I just try to add my idea here that the battery can be treated as an infrastructure. If
Well,
but currently there are a lot of difficulties, and it is not applicable at all.
Yeah.
Sergio, you're absolutely right. Batteries will be part of the infrastructure, but not in the kind that they are stored and changed like Duracell batteries. The Better Place project Daniel mentioned failed, as you have to store a lot of batteries more than used on the road. And if you store on the petrol station 4 or 5 batteries of your car, the sixth car which will come will also not have a full battery. So you have a lot of stranded costs stored at the local station. And as the charging power, and for example, the Porsche Panamera has a charging power of 300 kilowatt. So it can store 300 kilowatt hours per hour, which means you can drive about 2,000 kilometers, if I calculate it right, with the energy you stored within 1 hour on the highway station. So we can do many things which would be obvious at the first sight by changing batteries with high power charging, without changing batteries and storing batteries and somewhere else. Well, the issues with the charging stations Daniel mentioned, see it as a challenge. Yeah, there's a lot of work to do. There's a very innovative part. The charging stations, the wall boxes are getting better month by month. I got one from a Dutch manufacturer, which is great. And I have one out in the field, which works with Windows CE, this very oldie one. So we make big steps forward. And the one thing with the credit card or the bank card or whatever, this is something on my opinion, I understand everyone who wants this, but we have very high costs by the readers and double the infrastructure cost by the small wall boxes. On the high power charges, doesn't matter. But the small wall boxes are doubled by the costs currently. And we are seeing alternatives which are maybe more attractive than taking out your card and paying directly, as we or the industry here is implementing ISO 15118. Michael from Audi might know this. It's called plug and charge. So you plug your car, and the whole authentication is done by certificate-based authentication, where the car, the charging station, and the charging contract company will fully automatically authenticate, like Tesla does. When you plug in your Tesla with powerline communication, the Tesla car communicates with the Tesla backend, and Tesla knows, okay, this car charges here and it costs 20 cents per kilowatt hour or whatever. And this is the future, in my opinion. It's not a card I hold on the reader, in my opinion. And then we can do this with much cheaper infrastructure than when a coin slot or a card reader or something like this. This is where I think the whole industry will move to.
Thank you. I need to interrupt you here because we have a very few minutes left, and we need also to take a look over the questions that the audience sent. Some of them you already covered, I'll go through them. There is one question related to the AI research. What countries besides USA and China are leading in AI research in Europe? Can anyone give a suggestion?
I'm not really in a position.
Yeah, here what I can say is, because I have some friends of mine there in UK. What I see in UK, there is a lot of research which are done in autonomous cars. So they have, so there are many, but the main part what I see is there. I don't know for Germany what is the situation there, but what I heard from AI director of Volkswagen, he mentioned that there will be like, he mentioned 10,000 new jobs for data scientists relevant to that area, which I was, where the hell these people are going to come? So, I mean, we don't have so many students coming from the universities. So I think Germany, because it makes sense for the cars which are there, and also UK because of the innovations. So these are the two main hubs which I am seeing in Europe.
Thank you, Sergey. There is one other question sent recently. What kind of infrastructure is active for this sort of development? I guess that the person here refers to what would be needed to develop this.
Well, the good questions regarding what infrastructure. We talked about some different. So if you
probably this is relevant to what is the current status now, and my understanding of this question is that the person is asking for the autonomous cars, what is the infrastructure, the current infrastructure. So we all know what is the current infrastructure. It is we don't have vehicle to infrastructure systems. We don't have so much developed roads with the sensors or lines on the left or on the right side. So more or less the currently, because we are struggling with the infrastructure, we are focusing on putting as much sensors as we can on the cars itself.
agree.
In order to read and deal with poor information outside of the car. So we try to take everything inside the car.
Yeah, but not only sensors, also I would say HD maps for localization and so on. So we try to solve these issues by a lot of technology in the car. And regarding infrastructure, what is developed at the moment, in my point of view, we have a lot of activities at the ISO to develop communication protocols like ITSG5 or CV2X. So the next 5G communication standard, there are we heavily active in the standards and also the infrastructure suppliers.
Thank you. I guess that now I need to stop the discussion because we already almost reached the end of the panel time. I want to thank you all for joining and sharing your points of view and all the really useful information. So now I'm giving the word to Stefan for the next from the live day.
Thank you, Jana. This was a really interesting discussion. there were so many aspects I haven't even been thinking about. So, and this Windows CE is really, this is still a shock in my bones.
Windows CE 7 is not so bad.
We'll remove it soon.
Yeah, okay, so this is more or less a ghost from the past in my house. So after this discussion, we will have a small break, and then we will slip through the boundaries of legacy systems with Kotlin and Spring WebFlux. So thank you everybody in this panel. It was very interesting. And again, thank you, Jana, who is from our friends, the Data Science Society. And yeah, I think now we go into the loop and everybody else gets a well-deserved break.
Goodbye.
Bye.
Goodbye.
Thank you for having us. Bye.
Bye-bye.
Bye.
Bye. So hello again after the break. I hope you all got your coffee. Now let's jump to the stage and slip through the boundaries of legacy systems with Kotlin and Spring WebFlux. Hi Alberto, hi Lucas.
Hi there.
I will be back for the Q&A and I wish you a lot of fun and get those legacy systems to behave, please.
Thanks. Okay. Good, so shall we begin? I'll just share my desktop. So first of all, thanks, Stefan, and hi, everyone. Wanted first of all to thank you all for joining us. I guess you could do, you could be doing something else, but yet you decided to join us. So thank you. And let's just talk about our experience using Spring WebFlux. Stefan has already introduced us, but here's my colleague Lucas, and I am Alberto. We are both software engineers at Porsche. And I guess a nice way to start the presentation would be kind of explaining what do we do at Porsche, right? And kind of the obvious answer to that is, yeah, we build cars. That's kind of what everyone knows us for. But as just said, we are software engineers, and this is a developers conference, so there's something else as well. And what Lucas and I, in our department at least, focus is digital services for kind of the smart mobility universe. And some examples for that could be the new Apple Music integration that we released with the new Taycan. Or, for instance, new features and new apps for your phone to interact with the dealers, to interact with your car, kind of opening, closing it, honk and flash, all these kind of features. But not only, and also some kind of new business models, such as Porsche Drive, which is a new subscription model that we have for Porsche customers in order to kind of drive different Porsches. And yet again, what all these services have in common is backend systems, right? I mean, what you end up seeing is usually the front end, and there's kind of a big piece that's hidden in the background. That's usually the backend, right? And here in the smart mobility, we have kind of backend of all kind. Just as a matter of information, we're currently using 1 terabyte of memory for running our infrastructure, and that kind of will be interesting for later fact. But talking about the different kinds of services we have, we kind of have some microservices that talk to each other. That's kind of a state of the art for everyone. We also have some systems that talk to legacy systems. Everyone can imagine, I don't know, these old data center or systems that are in the factory or systems that are just running in other places that usually respond not so fast as modern systems. I guess everyone can relate in their area. And then we have some other systems, for instance, that take care of the communication with the cars. That's kind of a different scope, but yeah, we also have them. Something to basically mention now is that most of them are based on synchronous blocking IO architectures. Name it Spring MBSE. That's kind of a technology stack that we have used for quite some time, and that's kind of most of our systems use it. And this kind of phrase sounds pretty bad, right? I mean, it's kind of, if you're not reactive, you're kind of in the Stone Age, sort of. But I'm not sure we really know what it really means. So let's just try to figure out. So the next slide basically is a theoretical comparison between what you would find on the left side, which is the Spring WebFlux stack, besides what you find on the right side, which would be the Spring MBSE stack. And on paper, they are not that much different. I mean, you still have concurrencies, not that you don't have concurrency in one or another one. You basically have a different way of dealing with requests. So instead of having one request per thread, you have one thread that takes, or several threads that takes care of several requests. And then you have a different interaction with IO. But the truth is, as long as you don't hit memory limits, or as long as you don't hit resource limits, using one or another stack doesn't make that much difference. Like, you have different architecture in your server, kind of, But at the end of the day, it's not that much different. You don't get it to be super fast. You don't get it to be super slow because of using one on another. It's just a different paradigm. So what's this big deal about being reactive that everyone is talking about? At least like everyone around me is talking about, right? Let's just try to figure out. For this presentation, we basically came up with a very small example that you'll get the link later on. And it's basically this. So some of you might be familiar with Java or Kotlin and Spring for some time already, and this might sound familiar to you. What we have in here is on the left and on the right, REST controller, which is just like a REST web service that exposes under the path ping an operation, a get operation. Both services, what they do is they go to a different service and they call ping on this different service. And then when they get the response, they basically respond back to the original client. The only difference is that the left one is based on the Spring WebFlux stack, whereas the right one is based on the Spring MBSE stack. So one is using web client, the other one is using REST template. And then this ping service that basically is the one giving the response. It's just a simple one. It's built on Spring WebFlux because we kind of expected already the behavior that we then confirmed. And we didn't want this service to be the bottleneck when doing the load test that we did. So this basically just exposes ping, responds with pong, with the only particularity that it takes 1 second to do so. Trying to simulate calling a service that doesn't respond this fast, kind of coming back again to these legacy systems, these systems that do not interact that fast with each other. So what we did for the load test was giving only 16 megas of RAM of memory to the WebFlux and to the MBSE stack. We tried to be a bit mean. That's also because we didn't want to set up a whole super massive load test infrastructure. It was just my laptop, basically. And the results were quite curious. So we have this basically graphic. And this is basically on the y-axis, you have requests per minute load. And then on the x-axis, you have just time. And then what you have is the yellow and the blue line represent the number of live threads per system. So you have the MBSE is the yellow one, and the blue one is the WebFlux, whereas the red and the green lines are indeed the requests per minute. So you basically can see that both start handling requests very similarly until they get to 750 or 700 requests per minute. And at that point, basically the Spring MBSE one just dies. It cannot handle more load. It's just basically with 16 megas of RAM, cannot handle more load, just dies. The graphic continues just because of the type of the query we used in Prometheus to get this graphic. And then WebFlux continues accepting requests. And the cool thing is not this graphic. The cool thing is the next one, which is basically how it continues. So you basically see that with the same memory configuration, 16 megas of memory, the same load tool querying these both services at the same time, you get the MBSE implementation to just fail dramatically, die at 700 requests per minute, whereas you get the Spring WebFlux implementation going to 7,000 requests per minute. Also nice to mention here is it's not the WebFlux implementation that failed. It was my laptop. It couldn't generate more load, basically. And then the other nice thing to mention as well is the number of threads. So basically, with the Spring MBSE one, we have 38 threads handling a maximum of approximately 700 requests per minute, whereas in the WebFlux world, we have only 12 threads dealing all the requests. And 12 threads are enough to handle 7,000 requests per minute, which is, I mean, given Netflix or like big players standards, it's not that much, but given that you only give 12, like 16 megas of RAM, it's quite a lot. So coming back to the question, what's the big deal of using reactive implementations or using WebFlux? The answer is clear, right? It's efficiency. And you can basically understand efficiency as many different things. One of them could be you can handle 10 times more load. That's it, and that's a nice interpretation. You can also run your services 10 times lighter. So instead of requiring 1 terabyte of memory that we currently require for running our services, we could run them with, I don't know, 1,000 gigas, or I don't know, 2,000 or 100 gigas. It depends, right? Or I don't know, it could be 10 times cheaper to run. You have an infrastructure and you can reduce the size of your infrastructure because it doesn't require that much resources to run. And that's kind of like the real deal about using WebFlux against using MBSE. Now, but there's always a but, right? I mean, it's not always so cool things or like good things. The but is efficiency doesn't mean faster. And the truth is, with the reactive implementation, you tend to get slightly slower response times per request. You basically see here, Hey is just the load tool, and we basically triggered 120 requests for each of the two services in my local machine in parallel. So they basically are influencing each other's load at the same time. And what we had is that the average response time for the WebFlux implementation was a bit higher than the average response time for the MBSE implementation. And it might not seem a lot, but the problem is when you start playing with reactive implementations and synchronous implementations, and you don't basically play with the reactive rules. So the moment you start coupling synchronous libraries or like libraries that do not follow asynchronous patterns into your asynchronous server with reactive implementations, your penalties on like having greater response times, greater being lower response times, even becomes more notorious. So it's a very efficient type of server, and it's a very efficient type of implementation, but you have to be very careful with what you do with it. Because the moment you start putting a lot of CPU load, or the moment you start putting a lot of interaction with synchronous libraries, all your benefits just go to the sink. They basically are gone. So yeah. Now, going back a bit to technical part, what's the real difference between the code? Because I mean, if you're familiar with the Spring Boot, they seem pretty similar to one another. And the key difference between our examples is basically the fact of using web client instead of REST template. And if you see, I don't know if you're familiar with Kotlin, but basically the return types are different. In case you're using a REST template, which is just a normal imperative like HTTP client, you get then a string as response. Whereas in a web client, you get a mono of a string. And that's kind of a new term in this presentation. What's exactly a web client? Web client is a publisher. And here's where things get interesting. And what's a publisher, right? I mean, it's very difficult to, not difficult, but we could be discussing a lot on what a publisher is. So let's just get the definition of reactive strings. Publisher is a provider of potentially unbounded number of sequence elements, publishing them accordingly to the demand received from its subscribers. And here's the key. Like the web client is not going to publish anything until someone doesn't subscribe to it. And that's basically the whole asynchronous reactive part of this, right? This is the magic. This is where the magic happens. I'll basically pass the token to my colleague, Lucas. He'll further go deep in the concept of publishers.
Yeah, thanks, Alberto, a lot. So then, yeah, so from my side, hi to everybody once more. Yeah, Alberto, I think, really showed us nicely how you can use WebFlux or asynchronous processing to improve your performance. So actually, I would like to go on with this publisher sample of the web client and to work on a little sample with you to actually come up with a detailed understanding of how a publisher actually works. And here I want to make it a little bit simpler, so we don't use some network communication, we just use file I/O, which is usually blocking asynchronous, right? Which also has the same semantics, so which means you call it and you need to wait until it's there, and then you can go on with the processing. So in the end, I would like to come up with an idea that we will have a couple of samples of later in different implementations. So the idea is you have a file somewhere on your file system which just contains integers, and then you have an application which is reading the file, and it only reads one integer, and then it processes this integer, makes some computation on top of it, and then it reads the next integer from the same file and does some processing and so on and so forth. And in the end, I mean, already talking like this, about it, I think makes clear that there is a lot of waiting time, some idle time in your process to wait until the data is there, so until the I/O is done. And first, I would like to really start with a very, very simple and naive synchronous implementation, how you could provide such a, let's say, file int reader, I call it here, sync file int reader, where you just read the file and then you return some number when you call the function read number. And mainly, I want to focus on two places here, which are important, I think, for this sample, which is once opening a input stream and yeah, having the file being ready to be read, and then every time I call read number, I read the file, read from the input stream, and check whether it's an integer. And if it's an integer, I append it to some data that I already read before. And once I encounter a white space or an end of file, I just assume, okay, I have read the integer and I return the integer. Here, how it looks like in the end is, yeah, like this here on the right side. So you start your application, then you do some reading, you read the file, you read the integer, and then you're back, right? So you can work on it with the data. And then again, you do some reading, and you have idle time to wait in your thread for the next integer and so on. I mean, still, you can improve this a lot. I mean, as I said, it's a naive implementation. So you could read the entire file at once, right? So you would only have one point in time where you would need to wait for the I/O to be there. In case it's a big file, you could read bigger chunks into the buffer. So you still would have a couple of breaks in between, but not that many. And I mean, the ideal solution here, in case you would go on with synchronous processing, would be map the file into the memory, so into the virtual memory, and just leaving all the work to the operating system with managing how it's modeled in your memory. Okay, this would improve it, but still, you would have at least one point in time where you would have to wait for your I/O. And remember what Alberto told you. So there's one thread, right, which is a dispatcher thread, which dispatches all the incoming files, on the incoming requests from your clients. So in case you would really wait here, maybe like a second or longer, so you would be at least 1 second or even more than unresponsive to your clients, which is a lot. So how to improve it? Yeah, well, the idea is actually being asynchronous, and that's actually all about being reactive here in this case. And also, this is a naive example. I will tell you why, but we will have more examples later. So actually here, what we do is, in contrast to the example before it, that we create an asynchronous file channel to the file that we are reading from. And the asynchronous file channel is from the NIO library, which is non-blocking, which means your thread still can go on until your file is actually read, or actually during your file is read, and you can just go on with that. And yeah, so how it works is mainly that you don't wait until it's reading, so until it has completed the reading, but you just specify here in this case a completion handler, which is nothing else than a callback. And I'm doing it in a similar way than before. I'm only reading 1 byte. That's a simple way, I think, for this example here. It is okay. So you could be more efficient here as well, right? You could read a bigger buffer. And yeah, what I do is the same thing as before. So I'm collecting all the digits, and then I'm creating a integer. Once I have the integer well prepared in my memory, in my internal structure here, I want to emit it to the client, right? In the end, the client here actually is not expecting the value as a return type because it's asynchronous, so we don't have a sequence flow here in this case, but we need a callback. So once I have read the entire the entire integer, I just calling the callback with the integer. So how it looks like is you have again your main thread here, right, which is the same thing as before, but in addition to the last example, we have all the file I/O handling actually somewhere else. Somewhere else here is a thread or a thread pool which is handling this. So which means your main thread is not blocked. And you can do some other useful processing here in between. And that's the main point. So in the end, how it looks like is you start your processing, you call here this read number method, you pass it a callback, and everything is run on a different thread. Then at some point in time, the callback is called, and you can synchronize it here, right? Actually, you don't even need to, because it's done automatically. That's a nice thing here. You don't need to care about logs and all that. And then you do it multiple times, and at the end, you are done at some point in time with it. And this is a so-called pull model. So which means, as I told you already before, we can improve this a little, right? So we can read bigger chunks, which is the first part. And the other statement here is that there's a lot of communication ongoing. So for every integer that I want to read, I have to invoke this read number method. I need to pass my callback, and then my callback is called again. So and that's a lot of overhead. So there is another method how you can do it. And that's actually the push model. Which is very similar in terms of being asynchronous, and the other parts are a little bit different. So I have again a very simple implementation here. So I this time don't read only 1 byte, but I allocate a buffer of whatever size. So in a perfect world, you will read the entire file at once. For bigger files, you need to split it again. Okay, but the main point is here that we read a huge chunk of the file, and then we we parse the data into integers. There is whatever kind of function which takes the buffer or takes the string building in this case, and just returns a list of integers. And on this list of integers, we just iterate on and call the callback for every integer. So, which means that there's actually, in a perfect world, only one I/O operation. And once this I/O operation is done, we have parsed all the integers, all the data, and we can invoke the callback. And at some point in time, we are back on our main thread, right? You could still improve it a little. So you could call the callback with a list of integers, right? You would need to change your contract with the client. But this would be the perfect solution in terms of communication overhead. Still, there is a real problem with this example, which is the push concept. So because of the push concept, we do not care about the consumer anymore. So we just push, and it does not matter to us. So it does not matter to the publisher how busy the consumer is. In case the consumer needs to do a lot of processing and is really under heavy load, we just push and push and push. And this is the one reason, for example, that system breaks at some point in time under heavy load. So what did we learn now? Well, actually that there are different solutions. Asynchronous implementation seems to be rather complicated compared to the synchronous one, at least from the point of view when you just compare the lines, the number of lines. And the sad thing is that actually no approach that I showed you so far is really satisfying, right? So there is always a problem. But there's actually something really nice, which is called back pressure. And that's a mixture of both worlds. So everything is based on asynchronous model here, but it's a mixture between pull and push. And that's a nice thing here. So this is how it looks like then in the end. You have the consumer here on the right side, and you have the data provider. And here are two terms that I actually, which are very important, that I introduced, which is a subscriber. That's nothing else than a client, and we have the publisher, which is the producer of the data. And you really need to remember those terms, because they will be very important later as well. And that's also the more or less the official term in the reactive world for how to call the entities in your program. And so mainly, how does it work then? You have a subscriber which says to the publisher, hey, I'm bored. I want to have something to do, so I'm requesting data. In this case, I want to request exactly one data item, which is a number. So the publisher pushes a number to the subscriber. And at some point in time, the subscriber says that, hey, give me 3 more numbers. And the publisher returns or pushes 3 more numbers to the subscriber. So usually you have this kind of communication every time where the subscriber is out of work. So it's done with the prior data, or it's almost done. Okay, and this is actually a really nice concept to reduce the overall communication. So you don't have after every item a new request, but also it takes into account that the subscriber is not overloaded. And that's actually the entire concept between all the reactive frameworks that we'll see in a second. So all this, unfortunately, is not my invention. It was already defined, and actually the idea is there for a couple of years already, and it's based on a paper called Reactive Manifesto. I don't want to go into details here, but I really suggest that you have a look and read it once. It's really interesting. Mainly what it does is it defines the 4 core principles of reactive systems, which are responsive. So reactive systems should be responsive, resilient, elastic, and message-driven. So that's really something that is defined there. And I think now in modern programming, it's also more or less standard. I hope at least that it is. And so this reactive manifesto does not define any technical how to say implementation or stuff like this. It's just a collection of ideas. But based on this, there is something it's called a reactive stream spec, and it's there for at least Java and JavaScript, maybe also for other languages. Honestly, I did not investigate that. But the interesting thing here is that it defines some, how to say, boundaries and some basic principles how a reactive framework should work and should look like, but still they do not implement it concretely. So I have here copied one sentence, which is really important. And the main part here is this, it allows the creation of many conforming implementations. And that's the main point. So there are different frameworks in the end that are providing reactive implementations in the end. How do they do this? Well, they provide 4 core types. And this is actually provided by the 4 core types of the reactive stream spec. And 2 of them you saw already, which is a publisher. You may remember, this is the thing that actually produces the data. And then there is a subscriber, and that's the thing that consumes the data. This is what I showed you before, and this is exactly how it works. So you'll see it in a second. Then there are 2 more types. One is a processor, and that's actually a combination of both. So it's a publisher and a subscriber at the same time, which makes sense if you want to chain multiple operations. And then there's something missing. It's the subscription. The subscription is mainly the part that is the glue between the publisher and the subscriber. So how does it work then in reality? So in real code, you have again here the subscriber on the right side, and mainly it says, "Hey, I want to subscribe myself to a publisher," which we have on that side here. And then so this is done by the subscribe method of the publisher. And at some point in time, once this is done, the publisher calls the onSubscribe method on the subscriber, and it passes a subscription which is created by the publisher. And again, so this is done to glue the subscriber to the publisher. And actually, we will see later, it's not only the glue between the subscriber and the publisher, but it's really the glue between the subscriber and the data that will be generated later. Yeah, and afterwards, actually, there's exactly what we talked already about. So the subscriber tells the publisher via the subscription that it wants to have data. So here it requests 3 data items, and then the publisher directly pushes the data items to the subscriber via the onNext method. And you will see this method later as well. That's the core principle of all that. That's pretty important, so please remember that during the next samples. And the next sample is actually the next step of our very, very simple implementation. Before, you remember the last part was the push implementation, or the push model that we implemented. And well, I have here a publish file and reader, which inherits from a publisher. So this is a real publisher in this case. In the end, I came up here with fake data, which is just a sequence of integers here from 0 to 99. What you have to think about is that this here would be actually an asynchronous implementation which would read data. And it's important that it's asynchronous because, again, remember, there's, for example, in our Spring frameworks, there is exactly one dispatcher thread, right? So if it would be synchronous, it would block. But here it would just take too much of space. So let's live now with the fake data here, okay? Then the main part is that you see here in the publisher is the subscribe method. And what it does is it accepts a subscriber, and then the actually single step that is happening here is it creates a subscription file in Reader. So that's the subscription. We will see it in a second. And it passes in an iterator to the data here. That's really important because if multiple subscribers subscribe, then the subscription that will be created later with the iterator is exactly the place where you find the relation between the link between the position in the data and the subscriber itself. Okay, so that's the important part here. Then on the right side, you see that we have the subscription, which is a little bit bigger here. Still, it's not 100% completed, I would say, but for this example, I think it's enough. So the main point here is there are actually two methods. There's the cancel method to cancel your subscription, but that's, I think, not that important now. But here we have the request method, and the request method again is there to offer the subscriber a possibility to request data from the publisher. And this is the most important part, I would say, in this example here. So how does it look like? How is it implemented? So every time a subscriber requests or calls this method with some number here, we iterate until we reach this number. So in case it's a 3, so we will iterate through the 3 next positions or items in our sequence and pass in the data to the subscriber via the onNext method. And mainly that's it. In addition, we also check whether the request is already canceled or not. In case we are at the end of our sequence, we also need to tell the subscriber that we are done, so that we are completed, right? So there is a call to on complete in addition. Good. That's actually the main part here. So one thing is still missing. I guess you noticed already the subscriber itself is missing. But that's actually here the most, or actually it's the least interesting part of our sample, because in the end, you just consume the data. So I just have a very, very simple implementation here, which just prints the data it consumes, or actually the events that are emitted, like on complete, on error, on next. In the onNext method, we also just request the next item, which can be whatever number, right? You remember? So it's not only a pull here, but it's a mixture of push and pull concepts. And yeah, the unsubscribe method is overwritten here as well. So in the end, what is the final result of it? That's how it would look like. So you would have a publisher, would have a subscriber, and the subscriber then subscribes to the publisher. And that's the entire magic that happens. That's the entire magic that you see. And in best case, you don't even see this. So if you use some frameworks, you will see in a second. And the main thing, or the very, very important thing here that you should also remember is, in case you don't subscribe to the publisher, nothing will happen. So the publisher will never start reading, and the publisher will never start producing data. And this is most often the problem if you start working with the reactive components, because you just forget to subscribe and nothing happens and we don't know why. Most often that's the problem. Good. Then, okay, I think this we can skip. We saw it already a couple of times, this diagram. So I have 2 more things to tell you before we'll hand over to Alberto again. So we use in our project, actually Project Reactor, which is the default Reactive framework in Spring as well. So it offers you 2 types, 2 publisher types, which is a mono and a flux. And a mono can have either no elements or 1 element, and a flux which can have either no elements or arbitrary number of elements, which is makes the life just easier later. Because if you know you have only 1 element, then you don't need to care about potentially additional events that are emitted. So it just makes life easier. But actually, there is not a big difference in this type. And the really nice thing about Project Reactor is that it offers you really a ton of operators that helps you to manipulate the publishers and the data streams. It merge, concat, zip, flatmap, map, cast operators, and many others. So here's a really simple example of mono. So again, mono is just 0 or 1 element. Here we have 1 element with an integer. And with just method, we just create a publisher. And with the map method, we just consume the event and create another publisher with the result of this operation. And don't forget to subscribe. And yeah, on the right side, we see a marble diagram. And a marble diagram is very, very useful if you have operators that are more complicated to understand them. So here you just see, you call the just operator with an element. And in the end, what it results in is a publisher with exactly the same element. So here it's pretty obvious, but there are more complicated operations or operators that you really need this kind of diagrams. Here's another sample with Flux. You remember, it's more or less a kind of list of elements. So here I create a Flux from iterable, which is in the end a sequence again from 0 to 99. So it will emit all the elements, single elements, which means map will be called with 0, with 1, 2, until 99, okay? And there is the corresponding marble diagram, which tells you mainly that you have some kind of list or collection, and it will be converted into a publisher, which emits exactly the same elements as you pass into the from iterable method, and also in the same order, which is important here. Good. Then the last part of this section here, which is the testing. So testing is also pretty interesting because everything is asynchronous, right? So you need some kind of tools that are preventing the test to exit before actually your publisher is deleted and all that. And in Project Reactor, there is a class which is called Step Verifier, and this helps you a lot with unit tests and also other tests. And it really exactly does what I told you. So it, for example, prevents the thread to exit before you're done with your with the publisher itself. It provides different methods to test the publisher's data, to test the publisher's signals, the state after the execution, and sometimes you also need to check time. Well, in the context of time, right? So it also helps you with testing time-based publishers, which is pretty nice. So otherwise, maybe if you have some publishers that are taking a long time, for example, a day, you would need to run this test for a day, and here you can just cheat a little and make this day being processed faster. Okay, so how does it look like in a real code sample? You have a test, and here you create a step verifier with a create method based on a Flux in this case, and this Flux contains exactly 3 elements, 1, 2, 3. And what we say is here that we expect that this Flux is emitting actually exactly those elements in this order, 1, 2, 3. And then it is completed. And completed means it needs to emit the complete signal. So the onComplete method must be called. And this is already testing. I think it's also pretty straightforward. Then there is another test. So here I create a mono with an integer with the value 1. And I delay the element for about 600 milliseconds, which means it takes 600 milliseconds to be processed. Again, I create a step verifier. I do the same thing as before. I expect that it emits 1. Then I expect that it's completed. And then I want to verify that it took longer or more than the 600 milliseconds. Okay, this is what I test here actually in this case. And then there's the last part here, which is the step verifier where I just check for an on-error signal. You know, I'm just checking. So we are running out of time, so I need to make fast. There's one more slide that I forgot. In the end, that's the most important part here, actually, of all the slides. I think you noticed that it's pretty complicated to come up with a publisher that you implement on your own. So there are a lot of things that you need to think about, you need to care about a lot of stuff. And there are, for sure, cases where you need to do it. But in case you don't need, then you should not implement your own publisher, just use what is there. And there are a lot of also factory methods which help you to create publishers from, well, how to say, blocking implementations. And there is something which is called the Reactive Streams Technology Compatibility Kit, or TCK, which actually defines a lot of tests that are corresponding to the spec, and they just test your publisher. So you see the publisher that we worked on before. So even if this was really simple with a lot of fake data, actually a lot of test cases are really green. So this is something that helps you to validate the correctness of your publisher if you come up with it. And yeah, so with this, I would give the token back to Alberto for the last part of our presentation.
Yes. Thanks, Lucas. Yes, so basically we move to the lessons learned part, and this is basically I think you've seen basically from the beginning what's the complexity of start working in the reactive manner, and there are a lot of things that we just didn't mention, but they also count. So this is kind of a small summary of things that we just learned the hard way. Because even though we did some research before I start moving to the reactive world, there are things that you just miss. And also I kind of, at least I'll speak for myself, I like to kind of learn by doing. There are some things that you cannot figure out while doing so if you have not kind of learned it in a deep level before. So in general terms, using the WebFlux implementation is kind of like it requires some time for learning. As Lucas said, there are some kind of counterintuitive things if you were used to use Spring MBSE before or any imperative kind of programming way of doing. And also debugging, which is kind of pretty useful when you start. It's kind of pretty difficult and different from what it was. You'll see some examples now that basically. But let's go through the kind of top 5, I would say. I would call it maybe top 3 things that you should have into account when start working with reactive implementations. So the first thing would be non-null values. And this would be basically a combination of Kotlin and WebFlux. If you remember the operator map, basically we have a publisher here, which is the mono_just_1, which is a publisher of integers that publishes just one element, being it an integer with the value 1. And we just basically map its value to null. So we basically will have a mono of type integers that publishes null. Well, this basically crashes. It doesn't work. It will basically fail in runtime, and it won't die, but you will get a very nasty exception. Which, by the way, it's really difficult to track because you don't get a stack trace as you used to. But yeah, that's one of the things. This example is pretty clear, but imagine you don't map it to a null directly, but a function, and a function that can return null values. And mostly it doesn't happen because mostly you basically cover the cases. But someday there's an input that you didn't take into account, that you didn't test, then it returns null, then you crash, and that's it. So that's something you have to take into account. Nulls in like in monos and map operators, they are really nasty to handle this. To handle. Next thing is some people, whenever they see, or some people, we basically, whenever we started seeing the problems with null, we said, well, let's then use empty as a replacement for null, such as what some people did with optionals in Java, like 4 or 5 years ago. Some people started using optionals instead of dealing with nulls. So we used empties, and empties come with a different issue. So in here, in this example on the right, we have a mono empty of type integers. And then we try to map the element that eventually will publish and multiply by itself. And then when we get the next signal, we just print the output of the operation. Problem is, this will never happen. Like when you get an empty mono, it doesn't publish anything. Even though you see the signature of the expected type of ID, which is the default variable name of the map operator for lambda functions in Kotlin in this case, it's an integer. And if you know Kotlin, it says it's a non-nullable integer. So it's not a nullable type. So it's a bit counterintuitive because you see there, I'm sure gonna get an integer, but it's a mono empty. And you don't get any compilation warning. You don't get any like thing that will basically make you suspect. Yet again, this is just examples, and you will never write this, but eventually you might have a function that returns a mono. And eventually, whenever you have an error case, you could say then mono empty. And then you have this kind of issues. So just be careful with empties. Next advice would be very careful with empties again. This we learned it the hard way as well. So we have operators such as concatenation, zip, and many others, right? And in this case, monoswip, what it does is basically generates a mono out of two different monos. So it couples them. The problem is monoswip does nothing if any of the publishers that it has to zip is empty, which basically yet again imposes the same problem as we had before. You will see that you will get a tuple of a unit and an integer, and none of them can be null, nor the tuple. But eventually, you will never reach the do next because one of the publishers is null; it's empty. This is even harder to track than these nasty stack trace exceptions that you get, because you don't get an error at that point. Eventually, nothing happens, and you don't know why nothing happens because you usually don't put logs on nothing happens, right? Do you? I don't know. Yeah, I mean, these are like super counterintuitive, at least for us, for Lucas and me, when we started working with WebFlux, that we kind of learned by doing.
Maybe one more comment. Sorry, Alberto, to interrupt you. I mean, in the end, as Alberto said, this seems to be pretty clear, but usually what you do is you chain a lot of operations, like you have the sample in the middle. And this is also a very, very short example. If you have an example which is pretty long, where you have different publishers that you just combine together for whatever reason, where you just have requests from or two different other dependent services, and you combine it together, and one of them is empty for whatever reason, then you just end up with nothing, and you really just don't know what to do and where to track the problem. I mean, this is how we started. In the end, I think today, hopefully, we are a little bit smarter and find these errors faster.
Yeah, exactly. I mean, you also have the or empty do something, and basically you can give default values when you get an empty operation, and you basically have these countermeasures to deal with this. But usually this is the kind of mistakes you start doing. Then there's another also kind of difficult thing to understand, which is the difference between assembly time and subscription time, which is what happens when you run the code for the first time, and when you start debugging and see that you pass through the code twice, sort of. You don't pass through the code twice, but you basically go once for assembling, and then you go the second time when the subscription is indeed active or happening. And this is a nice example that Lucas and I came up with, explaining like how counterintuitive it could be. So we have an operation which is called get name from database, and then another one which is get name from the internet. Okay. Get name from database returns just name, and get name from internet returns my fake name. And they both are kind of publishers. They return a publisher. What happens here is if you run this main method, you'll see query database one time, query the internet one time, and then name. And then you say, well, isn't it switch if empty? Like, shouldn't get name from the internet just be run in case get name from database is empty or null? Well, cannot be null, empty. But this is the kind of difference between assembly time and subscription time. So switch if empty triggers on assembly time the execution of get name from the internet, which basically means you start the main method, you trigger the get name from database, you get the execution of get name from database, then you go to switch if empty, you get the execution of the switch if empty, you continue, then it gets the subscription. Because get name from the database is not empty, you just do nothing with the result of switch if empty. But you get the execution of that. And you can imagine some sort of cache, very simple cache implementation in which you basically always go to the source, and you never, like, it doesn't matter that you have the value in cache, but you always go to retrieve it again. That's very counterintuitive. A way of solving it is just basically deferring the execution of the method to the subscription time. And that's basically what happens in here. So just by adding mono defer and running this code, you get queried from database one time, and then the name. And that basically makes the execution of get name from the internet not happen until eventually subscription time. And that's basically what makes it not be executed if not needed. Of course, if we now make the get name from database to be empty, we get again the query the internet one time. And that's what I would expect from the beginning. But this mono differ is what basically, I don't know, we missed at least. And then the last example, now I close it, is about caching. And this is kind of quite interesting, and it could be even lead to philosophical discussions, because what is it that you're going to cache? So we have a method in here that basically just adds one to an element. It's just that it takes a lot of time to add one to an element. So if you pass 10, it will take 10 seconds to tell you 11. So it kind of looks like a good candidate for caching, right? Because for input 10, the output will be always 11. So let's just cache it. And since we are in the Spring world, you will be familiar with the cacheable annotation. Super nice. I've used it a lot of times. Works super well. So let's just put it there and see what happens. What is it that just happened now? What is it that we just did? What is it that we just cached? Like a promise of getting a long value? Like the long value itself? Like what is it that we're caching? Because a mono says that it will publish not, like it will publish 0 or 1 elements. And just that's it. So are we caching the promise, or are we caching the execution of the promise, or are we caching the value? It's kind of tricky to answer, right? The answer is basically you're caching the promise of the execution. So it gets on, yet again, coming back to this assembly subscription time, the execution will come in here, will assembly the mono, and that's what will be cached. What happens is that you start calling the service and you see that the cache does nothing. Your first request takes whatever seconds it takes, and your second one takes the same amount of time, and the third one takes the same amount of time. And the only thing you're saving is the assembly time, because the subscription time still executes delay element and still executes map IT plus 1. What you have to do is basically turn the cold mono, which is kind of the way of calling these monos, into a hot mono. And by doing so, you have to add .cache at the end. This is kind of counterintuitive. What you do by so is you basically turn the evaluation of the mono itself to the assembly time. And so you basically, effectively, you're caching the result. You're caching basically a mono that publishes the result value, not a mono that executes something that then returns the value. This way, basically, for the second and subsequent request, you get the request working properly. And the conclusion is that, I mean, caching, it's always a delicate topic. I have some colleagues that are they are very careful when caching something. And it's true, because invalidation is one of the most difficult things in the world. So if it wasn't already a challenge, it becomes even a bigger challenge. And that's like, this example only takes into account in-memory caching. If you have a distributed cache, a database, something that you have to serialize the data, it even becomes more difficult. And the problem is the frameworks, even though they have almost 2 years old, not all libraries are already like ported or implemented in a reactive way. And currently, there are no cache implementations that work reactively. So eventually, if you want to integrate Redis, for instance, you have to build it yourself. There's no add cacheable annotation that works with a Redis distributed cache in a Spring. And yeah, that's something you should take into account as well. That's it on our talk. Thank you very much for your attention. And I think we still have some minutes for some questions, so feel free.
So, thank you. We already have some questions. Can you stop the screen sharing, please?
Yeah, if I manage to do so, yes.
Yeah, you manage caching, so no problem. So, the first question is, how do you manage the Flux system with memory if there is no way of expanding it?
What? I'm not sure I understand the question.
Me neither.
If, like, are we talking about WebFlux and the load test that we did with this 16 megas of RAM? If so, what happens is that it's super efficient. It doesn't require more resources to run. And just with these 12 threads, which are basically the entities that take more memory into computation, are enough to handle all those requests. But I'm not sure if that was exactly the question.
Well, I hope so. We'll see if there is a follow-up comment. Next one is Benno. He says, thank you for using the term gazillions.
You're welcome.
But Benno, this is a technical term, like ginormous. Yeah, have to use
it.
And the next question is, do you use random test data?
Well, the answer is actually, it depends on the project. So, I mean, we started in the same project with Alberto. Now we are doing different projects, and I think everybody is, and also, I mean, there are also other people working in the department. I think different people also have different notions of how a test should work. And in the end, for us, it does not make a difference, I think.
Yeah, my only comment would be, as long as it's reproducible, yes. Like we basically, in everything we do, we try just to make things reproducible. And if you basically have random states that you cannot reproduce at a certain moment when you want to analyze them, then the benefits you could have by putting random data in are just gone, because you just lose a lot of data, like lose a lot of time tracking, trying to figure it out.
Okay. So I think we answered the question because we got an okay. I also have one last question. How did you guys get into Kotlin?
Well, actually, that's yeah. Well, it more or less was an accident, I think. I think, at least from my side, I did already Kotlin before, and I never was doing a lot of Java, so I like Kotlin very much. And in the end, it was not very hard to convince the others to try something else, something new. And this is how we started. And I think in the end, it really turned out to be pretty nice, because Kotlin is much more efficient in terms of, let's say, amount of code and doing actually what you want to do. And also the combination of Kotlin and here with WebFlux, it just matches, because you have this kind of flow in your functions, where you just have one function and another mapping function and another function. So it's just a chaining of calls. And this works perfectly fine with the lambda syntax of Kotlin. I think that's pretty nice.
Okay. Good. You want to add something?
No, not really. I mean, same experience as Lucas. We just like had some experience in the past in like very small things, and since we started this project together, we just decided to go for it, and it was like, I think, the best decision we could take. Like, it has a lot of benefits. Null safety is one thing that helps. Also, extension functions in the matter of WebFlux and chaining, which is just what Lucas just said. It's very cool. Like, if you look at our code, we have like some extension functions for monos, for fluxes, for this kind of thing, error handling. It's quite intuitive.
Okay. Thank you. And also thank you for your lessons learned. They were really, how would you say, insightful, you know? I will never be able to look at nulls and empties with my blind eyes.
Okay.
Thank you for that. And thank you for your talk.
Yeah, so thanks to everybody again for participating.
So for the audience, we will be right back with Alvaro, who will help us implementing continuous delivery in a data processing pipeline.
hello.
And
I'm
back,
and we will
soon
talk
talk
with
Alvaro
Martin
Lozano.
Lozano.
And
Finally, I will learn how to implement continuous delivery in a data processing pipeline.
Hi,
Hi,
Alvaro.
Hello.
The stage is all yours. And
Okay,
I'll come back for the
Q&A.
Q&A.
Thank you. So, welcome everyone to the talk. I'm Alvaro Martin. I work in the Data Lab. I don't know if many of you know the Data Lab. It's a part of the Volkswagen Group, so we are a member of the Volkswagen Group. We are also part of the Software Innovation Center, so it's more like a research area. And my background is mainly software development. I've been working for the Data Lab for already 1.5 years. And yeah, I want here to present you a talk that is more like a story of our experience implementing continuous delivery. And a data pipeline is not meant to be like a guideline on how to do things. I'm not a guru or anything similar. I just want to share our process and the problematics that we found and the good things that we found on it. So let's present a bit what the Data Lab is. The Data Lab, it's, as I said, part of Volkswagen Group. We work with all the brands within the group. These are our clients. And basically, we provide the solutions for them to any problem that they could have related to data. So whenever they need to solve an issue where the data is the main topic, we can solve them. And in the past, it has been a research area in a place where we demonstrated that we can do it. That was our motto, or we can do that. It was an area where there were a lot of proof of concepts, but not real products being implemented. So we demonstrated that, which things can be done with the data, how we can apply the latest technologies to try to find out the best way of using it. And the scope changed more or less at the same time that I joined the Data Lab towards, okay, you demonstrated that you can do that. Now let's change the motto to let's do it. And now that we proved that we can do that, we are focusing on creating the product that are actually working in the production ready, and that solve these issues. So the Data Lab is located in Munich. This is our office. You can see it there. We have more than 72 members working in the office. Among them, we have more than 20 nationalities, so it's a pretty nice environment. And we have been working with more than 160 projects, and we speak more than 22 languages. And like, if I don't say this, they will kill me there. We are hiring, so if anyone is interested at the end, they can check the links that we have. These are the 5 main areas within the data that we work. We have dedicated teams for them. So we have one that is advanced analytics, that is more related to the project that I'm going to be presenting today. We have another one that is natural language processing. We have really quite good experts there of natural language and how to automatically process, get the most out of it. We have a deep learning team that is focused on deep neural networks. It's also quite an interesting area. We have also even a quantum computing team that doesn't do only the theory part of it, but they also collaborate with Google and D-Wave to do some project with them. And we have a really strong AI research where people are doing their PhDs there, and they are releasing new papers into different conferences, different journals. So once I already presented the Data Lab, let's present the topic of this talk. I'm sure
that you have heard the word continuous delivery millions of times by this point in time. It's not anything new. It's something that has been applied already with success in multiple projects. So let's first define what we actually mean by software, continuous delivery in software, and then I will present more or less the differences with our implementation that we have to deal with. So the first thing, I think that the first point is what really defines continuous delivery. The deliverables are not delivered anymore in a planned way where you have a fixed point in your calendar that says this day we are going to stop our development for a time. We are going to stabilize the solution. We are going to talk to the client, and we are going to say, okay, here you have your new version, and this is the list of new changes. No, continuous delivery aims to be delivering in a continuous way. It could be even different times per day. So we move out of this planned and fixed timings to something more agile, more dynamic. And to do that, of course, you need the second point. That is actually, you need to add your small increments in a quick way to your, integrate them into your solution. For that, you need what is called actually continuous integration, and it's a requirement that you need for this. But there are 2 points here that I want to actually specifically define. One is deliverable. So what's a deliverable in software? A deliverable isn't anything but what the client expects at the end to receive when they pay. So they are paying you for a solution. They want to receive something in exchange. It could be software. It could be a binary. Let's say, for example, the application that you use to edit your pictures at home. You have a binary, you install it. That could be a deliverable. It could be source code. Imagine that you are working in a library that is used in the open source world. So what you are expected to deliver is actually the source code that will be used by other people. And that's one part of the deliverables, what it can be, that's software. And then you can also have, if you are the owner of the running solution, in this case that we were talking before, the client takes the binary, installs it in his own laptop or whatever, you are not the owner of the deployed solution. But you can be the owner of the deployed solution. Let's say you are a web service, a web shop. The client doesn't care about the software that you're running under it. The client wants to access your web, and then you give them access to the website and IP address or an URL, whatever. And that's the software that is being used. And it could also be, like it's in our case, that the deliverable is the data. So in our case, the client doesn't care about the software. It doesn't care about if it's Java, if it's Python, if it's anything else. They don't even care where it's running, if it's running in the cloud, if it's running in this or other environment. They don't care how many instances you are using to run it. They just care about the data that is delivered at the end. And these 3 different ways of defining the deliverable changes the way that you implement continuous delivery. So the second part of the word is the integrated, and then is where we have to actually talk about the path towards continuous delivery. I think that also this image, not exactly the same image, but the concept has been already talked a lot of times. To reach continuous delivery, you have to follow a series of steps. The first thing is to have your code under the version control system. Can be Git, can be any other system. This allows your team to work in a collaborative way to solve all the different features, all the different new commits to your code, and then work all together in one single product. Once you have that, you go to the continuous integration. This means all the time that any new feature is developed, you don't wait for a fixed date to actually integrate everything, but you have a build phase that is triggered automatically with each commit that actually checks that this new feature integrates well with the rest of your software. It runs the build, it compiles, it runs some tests, could be unit tests, it could be even the integration tests. And you can stay there as far as if your aim, let's say, is just the to deliver binaries, because then the output from this step could be directly the binary that you are delivering. You just put a label with the version and you give it to the client. And that's what actually comes with the third point. Like you just label it, you put a version, you say, okay, this is version 2.5, 2.6, 2.7, you can label it however you want, and you deliver this. But when your delivery is data or your delivery is the website itself, you can go one step further. And that's what it's called continuous deployment. And you can deploy the solution also to production in a continuous way. So whenever you have your binary tested, versioned, everything is going well, then you run a new step that is actually deploying this software somewhere. Or in our case, for example, it could be send this data to the final system where it's going to be used. Knowing this, now we are going to speak about our own implementation of this continuous deployment that we did for the data pipelines. This is how it looks like, the pipeline. I think this is pretty standard. It just has some 5 steps. The first thing is to build the solution. Like we were saying, this is the second step on the road. Of course, we are using a version control system. This build just compiles, runs the unit test, everything is okay, you can move to the next step. You run integration tests in local. That means, in our case, we are using Spark. So we take the Spark engine, we run it in memory, and we do some integration test on the same machine. Then, whenever everything passes, we go to the next step, that is deploying in staging. Staging is an environment that is exactly the same as deployment, let's say, a copy of it, with the difference that we are using testing data. So the data input that we get is just some either randomly generated data or acceptance data that comes from our PO. Whenever this deploying in stage is done, this is just sending the job to run. We run a smoke test that is actually going to the results of this deployment, to the data that you generated, and checking that some data is present there to confirm that the process went well. And then we have the last step that is actually to deploy in production. You can see that the last arrow is orange and it's not green, and it's because of a reason. The other steps are all automatic, and this step of deploying in production is at the moment manual because of some reasons that you may find. The first thing is that we are not sure enough with a single smoke test that the results are good enough. We need right now our product owner to give us the check that everything is okay to be able to deploy to production. But another thing is, you will see it in the following slides, we don't want to deploy to production in some scenarios. So this is just our pipeline. We are creating the version that we are talking about in the build phase. So in the build phase, we generate a version that is just a number, and we pass it to all the steps. So you know which version you have to put to your binary, which version you have to test, which version you have to deploy, and which version you have to smoke test, and which version also you have to deploy to production. And how does this version looks like? First of all, we are doing a trigger of the build on each pull request. And this is the case, for example, where we don't want to deploy to production. This is actually if you can see here, this is the name of the version. This is actually from a branch that is not the master one. So the name of the version is usually branch, in our case, build number, and then git hash. The git hash is not really, it's not always a good practice in all the books, but we find it useful to always be able to go back to the code and check exactly which thing was running in our code. So the difference here is that the branch is, for example, a feature branch. This branch has not been merged yet to the production environment, to the master branch. So we want to test all the pipeline before even merging this code into the master branch. And of course, this runs, we don't want to do automatically an automatic deployment to deploy to production, sorry. Because this is not the master code. This is not the code that we are going to be, let's say, sure that everything is working perfectly. So whenever this pull request gets reviewed by people, gets merged, because it passed all the tests, it's good quality and everything, everyone in the team agrees that it's good enough to go on, we push this to master, and this creates a new version that now is named master. It has also the build number of this branch itself, and it has also the git hash. And this one is actually the integration of this feature branch into the master code. So here we can be sure that everything is integrated. We can pass through all the steps, and if they are all okay, we deploy to production and we release this new change. As we were saying, as we were talking, our delivery is data. So it's important to see here what we are producing in each of these steps. So in the build phase, we just produce the binaries and some scripts to be able to deploy. The integration test is just a check mark saying, yeah, everything works as expected, or a stopper. You cannot continue in the pipeline, there is a problem. Then we deploy to staging with the test data. And this deployment to staging means we create a cluster on demand. We are working in the cloud with AWS. I don't know if you know the service EMR. You can create on-demand clusters. We just create a cluster on demand. We run the job there, and we create a version data. And this is the important thing here. So the data that we are producing is versioned, is labeled with the same version that we generate in the build, and it will be different for each run. Then, if everything goes well, this smoke test will actually check that in this version data, we have the data that we expected. If it checks, then we have the okay to deploy to production. Of course, we ask our product owner right now, because we don't have enough confidence, we don't have enough tests to do that automatically. But we check, is everything okay? Yeah, everything good. We deploy to production, and the same thing that happened in staging happens now in production with it's running in a different cluster, it's running with a different data, and it's taking longer because we have bigger amount of data in there, and then the version data is actually the one that we release to our client. So everything really nice, but you can still think, how does this look like, right? What's a job running on staging? What's the version data? What's the input? How does it work? So this is how it looks. Let's say the concept for us of a job. A job is nothing else but a function that takes some input, let's say in this case B, takes also some input parameters like the configuration of the cluster, where to take the data from, where to run, and all these kind of things. And it produces an output B prime in this case. I call this preprocess, but it could be any kind of job. So even though it may seem really simple, the image, it has a lot of concepts that are not easy. The first thing is the versioning in the output. So as you can see, in our case, we are generating files. They could be Parquet, ORC, different formats. And we consider the version as part of the directory where we write. So for each new version, we create a new directory and we create there the data. We dump there the data. I don't know if you have been working in systems before, in SQL databases, where you had to use some versioning system similar to Liquibase, where you version the data by managing or creating your own scripts to move from version X to version Y. You have to do some modifications of the state of the data. You have to move to be able to move the data from version X to version Y. And you also have to provide the same scripts to do a rollback. So you have to also engineer yourself. Sometimes it could be really complex, especially if you are changing some primary keys. You have to also write the code to move from version Y to version X in case that you have to do a rollback. That for me looked really scary. I used it sometimes, and it's a source of a lot of problems, especially if you don't take care on testing that extremely well, because it can corrupt your database. So we made also another decision that will save us all these problematics. We didn't want to go in this way. We went into immutable data. So we took the same concept that we have in functional programming, where you don't have variables, you have values that don't change in time. And we said, okay, our data is going to be immutable. Whenever we produce a data, it's versioned, labeled, and never changes. So if you want to run exactly the same pipeline with a different binary, you are not going to update the existing data, but you are going to create a new version, and you are going to keep also the previous one. That helps you to have a really easy rollback. So whenever you want to roll back, it's just a pointer to the previous version. You don't need to care about modification of states. You have a really easy way to audit what's happening. So if some person comes with a bug, you can easily reproduce what caused this bug, because your process itself is idempotent. So if you run it again with the same data, because they is immutable, it didn't change, it will produce again the same results. So you can actually do an easier debug there. And if we take a look on here, the input is immutable, the output is immutable. The only thing that we can change to change the behavior are the input parameters and the binary that we are running. So in the input parameters is where we are actually putting where to read from, which version to read from, and where to write to, which version we are writing to. And this looks really simple in one single job, but the problematic comes when you have something like this. It's really easy with one single job. What happens when you have to chain the jobs? Let's say that you have a job that takes A and produces A prime. You have another job that takes B, produces B prime, and then these outputs are the input of another job called aggregate that will just correlate these two data, do some aggregations, and output O. Now we have something that looks a bit more complex. If you start to think, okay, now I have to have a way of telling via the input parameters that this job aggregate needs the new version of A prime and the new version of B prime. So it's not that easy as if you have just one single input source where you are updating and you are outputting to one single source. This is fixed. Now you have, with each new version that you are releasing, and we are following continuous delivery, that could be quite often, you have to change these input parameters and link them together. At the beginning of the project, we thought, okay, this has to be something really simple. For sure, there is a tool that does that. And we thought, yeah, the continuous delivery platform, the continuous delivery platform that we are using has to handle this really easy. And the fact is that it's not like this. So this is actually right now one of the main topics that we are trying to work on. And we think in different solutions. So right now, because the complexity of our project is not really big, we decided to store these versions in the version control system. That means whenever you want to deploy the new version of this job that will take the new output of these jobs, you just create a really small pull request saying, okay, now you have to take this input and this input. You push, this creates the build, this creates a deployment that runs with these new dependencies. Of course, that's far from optimal, especially if you have a lot of jobs that are connected to each other. It kind of works right now for us. Maybe in the future, when we have more complex scenarios, it may not work. And then we were thinking on other different ways of doing it. Keep in mind that this is something that we were also looking on the current status, and in all the maturity levels metrics, they say that this is still into trial, so there is no defined platform to do these kind of things. The second thing that we thought that was the initial idea was to chain the deployments in the CI/CD and just pass the version. So let's say you have this job that whenever it finishes, it produces a prime. This is a dependency for our aggregate job. So whenever we finish here, we just say, hey, you now are able to use this version. So you would have the option to actually trigger this other job based on this version. Because of the limitations that we had with our CI/CD platform, that wasn't possible to do at all. So we had to discard it unless we change the CI/CD platform that we are using. Another idea that we have is to just chain the latest and keep the ability to deploy with different inputs. What does it mean? We keep always for each job the latest version that was produced in a file. So whenever the next in the chain has to be deployed, it will actually check there and it will know which version to deploy. For us, it's really important not to really communicate directly the jobs because we want to keep them independent. So we want the jobs to be asynchronous, to be able to be deployed at any point in time, because maybe, let's say, our job that is calculating A prime, we need to run it every day. Our job that is calculating B prime, we need to run it every week. And this aggregation only happens once per month. So we don't have the need to chain everything because there is no need to do that, and it's actually wasting resources, let's say. So this could be a good way of doing it. And another thing that we thought also is to use any kind of framework that allows you that, but then you lose the ability to label the versions from the continuous delivery platform. You have to come up with a new way of versioning. And we're thinking also using some kind of PubSub where you actually, your job puts in this PubSub queue, we are in the last version of this is X. Whoever needs to take my data, just consume this version and use it if you want. And then the dependent job could just read that and trigger itself. But again, you are now giving the ability to deploy to the framework itself and not to the CI/CD pipeline anymore. So this is a really big change that we didn't want to do right now. So given this context, we found out some advantages of following these principles. First of all, is that we can compare really easily each change. So because the data is immutable, because we are generating a new version of the data on each run, we can easily compare the results of one run with the previous one, or with one run that was done 1 month ago. We are also calculating some metrics that give us more in-depth review or in-depth, let's say, view of what's happening in the data. We can also compare them because they are also versioned. And this is something really, really nice that if we wouldn't have this setup, it would be harder to do. Another pro is that we can reproduce the past. So whenever we trigger a job, we know the input parameters, and that's all what we need. So in the input parameters, we know the binary that we are going to be running, which data we are going to take as input, and which data we are going to be producing. Whenever you use this parameters again, you will have again the same results because your input never change. You will always get the same results. So you have this idempotency and the ability to go back and debug anything that was going bad. You can audit the changes for the same reason. So whenever you have a new change, you have an audit of what's happened, and you always can go back and check what's going on. That allows you to have way more speed in the new features and bug fixes. So if you want to check the comparison, for example, of performance on a new improvement that you thought, you just run the new job, you run the old one, you can compare really fast the results, you can go to the metrics, you can see the comparison directly of all the metrics. And if you don't think, you think that maybe there was something wrong in the cluster at that point or whatever, you have the ability always to reproduce it again. That reduces also the errors due to human interaction. So as you saw, all the processes are automated. Everything happens triggered by a machine. And we only keep these small parameters to be changed by the software developers, which is something that makes your software more robust, of course. And the last point that we have quasi-instantaneous rollback. So if the client comes and says to us, hey, the new version, the data is totally bad. It's missing, one table is missing half of the data. Another table is outputting something that is totally wrong. Just by going back to the previous version and exporting that version, we have this problem solved. It's really fast, really quick. You don't need to mess with changing now a lot of things that happen in a state. You don't keep any state. You have everything is almost stateless. You just roll back to the previous data, and that's all. But of course, there is no free lunch. There are some problems that we found. The first thing is what I was talking already. The orchestration is quite complex. You have to find a way of communicating this new version delivery between the jobs. That is, we didn't find any existing tool that is already doing that. It requires extra development in tooling and automation, of course. You have to keep your own CI/CD pipelines in a good way. You have to engineer your deploying the scripts so they take into account this versioning system. It has a bit of complexity. And of course, it increases the data generation. So if you are only keeping one data output, one data input, and you are updating it, you have the minimum data you need always. If you are creating a new version with each run, the data generation explodes. That can be mitigated. For example, if you are generating data from a pull request, you can always output that to a different branch of your directory structure and then have some kind of purge there, so you can clean up these directories. And you can also, if it gets really out of hand, you can always keep only the last meaningful runs that you would think that it will require for you to come back. So for example, the last month, the last 2 months. So it's something that can be mitigated. And right now in the industry, I think that the main problem is not the storage at all. So it's quite cheap right now. So it's not the biggest issue here. So given this, I think I finished my talk. I have to say you thank you. Here you have the links if in case you are interested on anything related to what we do, if you want to apply to any of our positions, and I'm open for questions.
Live in 3, 2, 1. Haha, here I am. Thank you, Alvaro.
You're welcome.
By sharing this screen, you already also answered the first question, believe it or not.
Oh,
what
that's good.
platforms are you on to connect?
Here.
Oh, this is really a great coincidence. But sorry, first I want to say thank you for your talk.
You're welcome.
It was very interesting and also made me think about stuff I do myself. Okay, but now to the question. do you use a prepared set of data to check your code?
Yes. So the data that we are using, first of all, we have different layers of testing. We have first the unit testing, where we just test individual classes. Of course, there we don't really care much about the data. We care about trying to find out the maximum number of cases that we can test.
Yeah.
So we are testing the corner cases, weird scenarios, and all these kind of things. Then we have a second step that is the integration test in local. This is more or less like a green light to say everything integrates well together, things are serializable, the classes connect together, there is no error there. So we have a really simple example. Then when we're running staging, we have let's say hard-coded input that makes sense. It's logically makes sense for the business. We run the job, and then we expect, of course, some output. That is what we check in this smoke text. So for example, we are saying, imagine that you are calculating the average age of people. We have a set of 10 people, we put their ages, and at the end we expect to have because we know already the result, we expect to have this average, and that's what we are checking. And then for some jobs, we just generate a bunch of random data just to test the corner cases whenever we have to do, for example, any parsing inside a string or something similar. So you want to have really weird characters there and to see that there is no problem with anything. So there we just launch a whole bunch of random data, and you don't check the result, you just expect that it doesn't crash and it produces something at the end. Mm-hmm. So this is like the different level of testing that we are doing.
So would you like subversion the code and subversion the data, also the data you test with, or?
Yes. So as we were saying, we have two different environments. One is testing or staging, and the other one is deployment. And we generate into two different, let's say, areas, a structure with the version of the run that we are running. So every run that we do, it versions the software itself, so the job that is running, and the output of the job is also versioned, which means you have a dedicated folder for the output of this specific run that happened in this trigger that was in the pipeline. And in that way, it's really easy for us to compare different changes that we do to the code. So if you want to compare two different ways of approaching a same solution, you can just create two different branches, two different pull requests. They will trigger two different versions, and you have then the results. So that's the way that we are handling this version. Mm-hmm. We don't only version the software, we also version the data.
Okay. So thank you. So next one is anonymous with thank you in capital letters. So I would actually need to shout that, but it's very late. I don't want people to wake up.
Probably a colleague.
Yeah, it's fifth talk of the day.
Oh, thank you.
And then also the question ETL tool question mark, which is actually not a question, because
I think that maybe it relates to if there is an ETL tool that can do this. I will take it as this.
Yeah.
I know that there is something like Airflow and all these kind of frameworks, but this we're actually taking a look on that. The problem that we found with that is that you lose the ability to run the jobs independently. So you can define a flow, and you can trigger the whole flow, but you cannot have the control over, okay, I will run 20 times the import of this, 10 times the import of this other thing, because if I don't have data, I don't need to run it. And only when I have at least one new version of all of them, I will run then the aggregation.
Yeah.
This example, for example, you cannot do it if you have an ETL pipeline, because as far as what I found, let's say, or what we found in our team, whenever you trigger something, you just trigger the whole pipeline. And there is no way of saying, okay, just trigger this, but with this data. And now I want to compare the aggregation, but try to, instead of using this version, use the previous one. Or now combine this version and this version. So this flexibility, we didn't have it with the ETL tool.
So basically what you did is also you wrote your ETL tool who works the way you want it to work.
Yeah, more or less. So it's an ETL that allows you to run all the jobs asynchronously and not dependent on each other. That allows you also to treat the jobs. Let's say I come from the software development world. I know the best practices there. I know the tendencies there. It's a way of treating the jobs as microservices. So they have a way to communicate to each other. They depend on each other, but they don't have a hard dependency. So the way that they depend on each other is just by sending some data. So that allows you to develop each of the job independently and not to, if you have a problem in the job B, you can still run the rest of the jobs with no problem. And whenever you solve this issue, you can run any of the previous versions that you generated with the other previous jobs. So you have this flexibility of being more robust and being able to run anything at any time that you don't have with an ETL, for example.
Okay. So next one is thanks for the informative talk. Enjoyed it very much with smiley. And then it's a very well structured and informative. Thanks. Hope to see you on future conferences as well. I think this is what I also hope for. This was your first talk, or?
Yeah, it was my first talk in a conference.
Well, now
Nobody.
that was a great first talk. So there are plenty of more to come.
Well, I will see. It was a first nice one, and yeah, I also like to share all what I learn every day. So that was the idea also of this talk. Try to share what we are learning right now, and instead of keeping it full to myself, maybe there are people that have different opinions, so maybe it can help also to other people. So.
Yeah. I think there are always different opinions, and it's good that they are.
It's good to share them, and
they make us think about our own opinions. Okay, so thank you, Alvaro, and
thank you.
Hope to see you in the future, and have a nice evening.
I will remember again, if you want to contact either me or the company, you just have here the information. Take a screenshot or something. And
yeah, it's in the stream. People can put it on pause and write down stuff on paper.
Yeah, also.
Yeah, but you know, it's a tip from my past. We are developers. We don't write on paper because we cannot read our handwriting. There's a reason why we use keyboards.
Probably, yeah. We are not used to read any paper anymore.
That's true. Okay.
Okay.
Bye, Alvaro.
Bye.
And for everybody else, we will be back sometime in the future, and this time in the future, echo is gone. So this time in the future will be the 17th of November, which is the third day, the last day of the mobility days. But there will be plenty of interesting talks again. We will have a look at artificial intelligence for autonomous driving outside the car. Do I have to drive on the roof? I have no clue. This will be interesting. And then also from Sergey Sergeyev, who we already met on today's panel about analyzing people's mobility in indoor locations like hypermarkets or malls. I already had a chat with him. This will be definitely very interesting because it's crazy about what you can think when you think about that problem. Then we will have augmented intelligence for transport planning and human in the loop modeling with Stefan Petrov. And we will learn something which is actually something we should learn at the very beginning when we look into machine learning code. We will learn how to debug it with Svetlin Penkov and how to build a food delivery app using location intelligence and metrics routing with Dosana, Olivia and Jose. So, and all of this will take place on 17th of November. But the best thing is that's not all, because right now you can also start to register for something which will come up in December. It will be plugged in right after I leave the stage, turn off the lights and stuff like this. It will be the Live Week from 30th of November to 4th of December 2020, and it's the 3rd edition. So this being said, I want to thank you all for your attention. Have a nice evening. Have fun when debugging. Don't rip out your hair. Bugs are part of a feature set. So, bye-bye. See you. Huh? Are you still there? You should really go now. See you next week. Bye-bye.